Let's play does it converge or does it diverge? Let's see if this sequence diverges. So we're gonna try to follow we're gonna try to find the limit of it. I think that the key here is to use the E limit formula. Now this says that if you have the limit as n approaches infinity for 1 plus x over n raised to the power of n, it's going to equal Euler's number raised to the power of x. Now here we have the square root of 1 minus 1 over 16n raised to the power of n underneath the radical. Now we should rewrite the square root as a power of 1/2. And this is just an interchangeable variable phi. If we have the square root of phi, such that the index is 2, so it's a square root, a square root of phi is going to equal phi raised to the power of 1/2. The denominator in the square root is just going to be whatever's in the index of the square of the radical. So let me go ahead and rewrite this sequence here. So we just removed the radical and we replaced it by raising it to the power of 1/2. Though the power rule, if we want to get this n and this 1/2 to interact with each other, we can do so via the power rule. And so a raised to the power of n raised to the power of 1/2 is going to equal a raised to the power of n over 2, because basically all that's happening is we have a raised to the power of n multiplied to 1/2, which of course is just going to be a raised to the power of n over 2. That said, we can go ahead and rewrite this again and then just bring it up to the power of n over 2. I think, pardon me, I think that we should actually rewrite it in such a way where it actually matches um the E limit formula. And what I mean by that is if we have 1 minus 1 over 16n raised to the power of n brought up to the power of 1/2. So if honestly if we just if we just undo what we just did, um I think that that might be better for this here. The limit as n approaches infinity for 1 plus x over n raised to the power of n, because this is the exact same thing. These are the same. Right, so if we look at like the inside limit here, if we look at like the inside, um, and then we want to just sort of like rewrite this so it matches the E limit form a little bit more, we could say that like 1 minus 1 over 16n will, that's the same thing as 1 plus 1 over negative 1 over 16 over n, I think. Right, such that here x equals negative 16. And then we can plug this directly into the E limit formula. And then for x we had negative 1 over for x we have 1 over for x we had negative 1 over 16. And then remember that this we're just working on this parenthetical statement here, this bracket statement here. So what we need to do is actually take this e raised to the power of negative 1 over 16 and we need to raise that to the power of 1/2, which is going to be the same thing as e raised to the power of negative 1/16 times 1/2, which is going to equal e raised to the power of negative 1 over 32, I think. And then that's going to be our answer. Let's say that we have a series. I'll add an infinite series. So let's say we have k equals 2 and it's an infinite series, and it's an infinite series of a rational expression with a square root in the numerator, the square root of k, and then in the denominator, the natural log of 9 times k. And we want to use the divergence test to figure out whether the series diverges or not. Well, um, we're going to use the divergence test, and the divergence test is a test that tests for divergence, but it cannot test for convergence. And just remember, like a convergent, if something is convergent, it means that it goes to a finite sum, right? It converges to a finite sum. Um, everything once it's summed up, right? Once you've completed your summation, it's going to equal a um, a finite number, whereas a divergent series, it's it's going to either be infinity or it's going to oscillate between numbers erratically in a way that's unpredictable. So let me go ahead and write out the divergence test so we can investigate. Okay, so the divergence test says that if you take the limit as k approaches infinity of a sub k and it does not equal 0, well then that means that the series diverges. So here we need to identify what is a sub k, what a sub k is. Let me just box this up real quick. All right. Um, I don't know if I got room here. Let's go ahead and try to squeeze it in there. We got a sub k equals the square root of k over the natural logarithm of 9 times k. All right. Um, we're gonna go ahead and we're gonna take the limit of that as k approaches infinity. So I'll say that the limit of as k approaches infinity of the square root of k over the natural logarithm of 9 times k. Um, we're gonna take the limit of this statement here. So as k approaches infinity, let's just kind of break this down a bit. Um, as k approaches infinity, right? If we start plugging in numbers, counting numbers that go larger and larger and larger into the positive direction, so positive 1, 2, 3, 4. If we start plugging in numbers for k, well, we're going to end up with um, the square root of infinity because we're just going to plug in infinity right into k. Um, sorry, I'm laughing because I couldn't draw an infinity symbol. Anyway, so I'm trying to draw with my mouse, you guys. This is just going to be infinity. All right. If you take the square root of infinity, if it's just going to be infinity, and as you start plugging in large numbers, larger and larger, for uh, as k approaches infinity, for the natural logarithm of 9 times k, and you start plugging in numbers for if you plug in infinity for k, right, larger and larger and larger, it's just going to go to infinity. And what this is going to give us is it's going to give us an indeterminate form of infinity over infinity. And the presence of this indeterminate form, here specifically can be dealt with using L'Hopital's rule. Um, L'Hopital's rule says that we can evaluate an indeterminate form if we take the derivative of the numerator and the derivative of the denominator. So we have a limit that yields an indeterminate form, and we're going to take the limit of the numerator and the limit of the denominator. So let's go ahead and take the limit of the numerator really quickly. And the numerator, of course, is going to be the square root of k. And the square root of k can be rewritten as k raised to the 1/2 power. So if we have k raised to the 1/2 power, we're going to take the derivative of that. We need to apply the power rule for differentiation, and that's going to go like this. And that's going to be equal to p times k raised to the power of p minus 1. And that's going to be the power rule for I don't like the way that looks. is going to be the power. That's going to be the power rule that we're going to apply here. So then that would mean that that k, that the derivative of k to the 1/2 power is going to be like this, equals 1/2 uh times k 1/2 minus 1, and that's going to be 1/2 times k raised to the power of negative 1/2. Okay, and so I'll just leave that one. That's a 2, by the way. So then well, I think that we should rewrite this. I think that we should rewrite this. So we're gonna say that 1/2 times k raised to the power of negative 1/2 can be rewritten. Um, what we'll do is we'll stick with this 1/2 out front, right? So we'll put 1/2. Honestly, I could probably put the numerator just like center that. This is gonna be 2 right here. But then if I move this k raised to the negative 1/2 power into the denominator, then we're gonna have k raised to the half power. That negative 1/2 will become positive. But then k raised to the 1/2 power, as we've established before, well, that's just going to be the square root of k. So this is going to be the square root of k. So 1 over 2 times the square root of k. Okay? Okay. Anyway, so then we're gonna do the denominator. Okay, so the natural logarithm of 9k, 9 times k, well, this is actually going to require the chain rule. The chain rule. And I say it like that because, well, the chain rule, me and the chain rule have a little bit of a history because it's not the easiest rule to apply, and so I try to be very organized upon doing it just because I don't want to trip myself up. Um, so I'll just go ahead and finish writing out the formula for the chain rule here, and then we'll get started on differentiating this. The chain rule it means to differentiate the outside function and then multiply it by the derivative of the inside function. So um I throw it in a box here. And let's try to identify first the outside function. Well, we're gonna call this f of u, and then u is the variable that's like the stuff that goes inside, right? So f of u, well, on the outside we have ln of 9 times k. So that would mean that f of u is going to be ln of u such that u is 9 times k. So then that would mean that the inside function, which we called g of k, is going to be 9 times k. And you might say, Stella, you just said that 9 times k is going to be u. Well, hold on, let me cook for a second. So if we have the natural logarithm of 9 times k, right? So like just a little apostrophe here. If we have the natural logarithm of 9 times k, and we're trying to figure out what this is in the formula, it's going to be right there. So it's going to be f of g of k. That's that composite function there. So first we are to differentiate the outside function. We're going to take the derivative of f of u. Um, so if f of u is the natural logarithm of u, and we want to find f prime of u, its derivative, we need to take the derivative of the natural logarithm of u. And the natural logarithm of u, well, that's going to be 1 over u. What that's going to mean is that f prime of g of k, well, that's going to be 1 over u. Well, we assigned 1 over u, right? So that's going to be 1 over u, which is the same thing as 1 over g of k, which is the same thing as 1 over 9 times k, right? So we're going to have to differentiate that inside function here. Um, and to do that, so we have g of k assigned to be 9 times k, and then to find g prime of k, we're going to have to do, well, this is a constant multiple rule, so we'll ignore that 9 for now. The derivative of any variable, in this case k, is going to be 1. So the derivative of 9 times k is just going to be 9. All right, that looks like a g. 9. Right. Okay, cool. So then what we can do now is we can multiply them. So we'll go ahead and we'll go ahead and we'll multiply them. And so that's actually going to be 1 over 9 times k, which is what we got from before. And that's going to be times 9, and we're just going to multiply that straight through, and we're going to end up with 9 over 9 times k. And um, and so now we have our derivatives. So now we have our derivatives, so we can apply L'Hopital's rule. That's that LH abbreviation right there. And um, and so maybe I should be a little bit more clear. The derivative, this here, what we just did, is the derivative, and then k is the variable that we're integrating with respect to. So the derivative of the natural logarithm of 9 times k, well, um, that's going to be 1 over k. Okay, so then what we're going to do is we're going to apply L'Hopital's rule. So we had the limit as k approaches infinity of the square root of k and the natural logarithm of 9 times k. And we took the derivative of the numerator. What do we get for the numerator? 1 over, oh yeah, okay. Okay, so we're gonna I'm gonna kind of put this a little bit lower just because we're gonna have a complex fraction. Um, so what did we get again? We got the 1 over, okay, so we got in the denominator 2 times the square root of k, and then in the numerator we have a 1. You guys can tell that's a k, right? That's a k. Um, and so then in the denominator, we just found the derivative of the natural logarithm of 9 times k, which is 1 over k. 1 over k, and then we're going to reciprocate because we don't want a complex fraction. So upon reciprocation, we're going to have this. Well, that's going to be k. That's going to be k over 2 times the square root of k, right? But then, and I'm just going to do it over here since there's a little bit of room here. Um, k over the square root of k. Well, that's just going to equal the square root of k. And the reason for that is because in the denominator, it's actually, remember, we have k is the same thing as, like, this is the same thing as k up, I'm just gonna do this up here, k over the 1, k to the 1/2 power, which is the same thing as k to the first power minus, uh, um, so k to the first power minus 1/2, which is going to give us k to the 1/2, which is the same thing as the square root of k, right? And so what that means is that we're actually going to have, this is going to become the limit as k approaches infinity of uh I think it goes like this. Square root of k over no, it doesn't go like that. No, it doesn't go like that at all. It goes it's oh yeah, no, yeah, it does. It does. The square root of k, um the square root of k over 2. Okay. But then what happens? What happens? So, well, if you plug in if you plug in the infinity, if you plug in infinity for k, it's going to be infinity. The square root of infinity is infinity over 2. If you take infinity and you divide it by 2, well, that's going to be infinity. So the answer to this is infinity, and infinity is not 0. So infinity, just write this out here. Infinity does not equal 0. 0 is the absence of numbers. Infinity is numbers forever. So, um, so what that means, right? What that means is that, well, that means that the limit of the square root of k over the natural logarithm of k times 9, or to be consistent, the limit of k as k approaches infinity of the square root of k over the natural logarithm of 9 times k. I don't really have that much room here. Let me just see here. Let me just move that little arrow there. I'm just gonna move this. Oh, no, doesn't want to do that. Okay, let's um let's see here. I think we can get this to work. There we go. Let's write in blue. So our conclusion is as follows. The limit as k approaches infinity of the square root of k over the natural logarithm of 9 times k equals infinity. And that does not equal 0. And so therefore, by the divergence test, we can see that our series, starting at k equaling 2, going up to infinity of the square root of k over the natural logarithm of 9 times k, it's going to diverge by the divergence test, and it's going to diverge because we have gotten an infinity here, and so that's our answer. All right, so let's say that we have a sequence a sub n, and in this sequence, right, there's a recurrence relation. All right, so a sub n has a recurrence relation, and the recurrence relation is defined as a sub n plus 1 equals um, 3 times a sub n raised to the power of 2 plus 2, and we're going to say that a sub 1, it's an a, that looks like an o, that's an a sub 1 equals 0. All right, so a sub n has a recurrence relationship, defined as a sub n plus 1 equals 3 times a sub n raised to the power of 2 plus 2, and a sub 1 is 0. A recurrence relationship, it's like a rule that tells you how to get the next term from the previous term. So here's the first term, this is the previous term, and we want to get this, the recurrence relation here, that's going to tell us how to get the next term. So that means that we're going to start with a sub 1 equaling 0, and we're going to find a sub 2. So a sub 2, we'll find a sub 2 because we know that n equals 1. That equals sign. I'm trying to be less of a perfectionist, but I just want to make sure you guys can actually read this. Um, n equals 1. We could say that we're going to have a sub 1 plus 1 equals, here comes my cat. Theta, please, please. You know, she comes right up to my computer and she just stands in front of it. Okay. Okay, so we got a sub stop, Theta, stop. We have a sub n, no, we have a sub 1 plus 1. And then that's gonna equal 3 times a 3 times a sub 1 raised to the power of 2 plus 2. Okay, but we know what a sub 1 is, right? We know what a sub 1 is, so that's going to mean that a sub 2 equals um, 3 times 0 raised to the power of 2, and we're gonna add 2 on the end of that. And so, well, that's just going to mean that if we do 0 raised to the power of 2 is going to be 0, 3 times 0 is 0, and if you add a 2 to 0, it's going to be 2. So that would mean that a sub 2 equals 2. All right. So then now we want to find a sub 3. We'll go up to 4. So let's find a sub 3. Well, we're going to use the rule that n equals 2, and we know the recurrence relation. So we're going to have um, a sub 3. So a sub 1 plus 2 equals 3 times a sub 2 raised to the power of 2 plus 2, and that's going to equal a sub 3 equals, and we know that the a sub 2, right, by what we found it is going to be 2. So a sub 3 equals 3 times 2 raised to the power of 2 plus 2. And that's going to equal, so 2 raised to the power of 2 is going to be 4. 4 times 3 is going to be 12. Plus 2 is going to be 14, right? So that would mean that a sub 3, I guess I could do a sub 3 equals 14, like that. And then lastly we'll find a sub 4 such that n equals 3. And we'll go ahead and plug into our recurrence relationship. A sub 1 plus 3 equals 3 times a sub 3 raised to the power of 2 plus 2. Um, and and so then that's going to be uh, 3 times 14 raised to the power of 2 plus 2. And then a sub 4 is going to equal, uh, well, 14 raised to the power of 2, it's 196. 14 times 14, I think it's 196 plus 2. So then 196, 196, 196. So that was going to be 12, 18, 18, 1, 10 plus 18, right? 10 plus 18 is going to be 28, 2, 4, 588 plus 3. So then it's going to be plus 2. This is going to be 590. So then this is going to be 590. A sub 4 is going to equal 590. No, yeah, 590. So, 590. So we have this sequence, a sub n, and we're given the recurrence relation. And we were given that a sub 1 equals 0, and we were given that a sub 2 equals 2, and then and then we were given a sub 3 equals 14, and then we were given that, well, we weren't given that. We calculated a sub 2 to be 2, we calculated a sub 3 is equals 14. We just calculated that a sub 4 is going to equal 590. So that's how you would do that. Okay, so we have a series and it's going from k equals 1 to infinity, and it's of a trigonometric function, cosine of um, the rational expression 2 over k raised to the 10th power. And we wonder, like, does it converge? And then we say, well, how about we use the divergence test? Because the divergence test says that if you have the limit k approaches infinity, k approaches infinity of some expression a sub k, and it does not equal 0, well, then that would mean that uh, so if you have the limit as k approaches infinity for some expression a sub k and it does not equal 0, then the series for a sub k diverges. Now just remember that the divergence test, it cannot test for convergence. It can be it can either confirm divergence or it's inconclusive. Well, here, let's go ahead with the identification of what our a sub k is. A sub k is going to be cosine of 2 over k raised to the 10th. And via the divergence test, we shall take the limit as k approaches infinity of cosine 2 over k raised to the power of 10. And then we're going to plug in infinity. We're going to plug in infinity into k. So as k approaches infinity, as k raised to the 10th power approaches infinity, um, we're going to get we'll get 2 over k raised to the power of 10, and that's going to approach 0 because we're going to be putting in larger and larger and larger numbers into the denominator. And when you have a numerator with a denominator and the denominator is getting larger and larger and larger, you'll find that the numerator is going to get smaller and smaller and smaller because it's division. It's the operator's division, so it's going to become 0. As it turns out, cosine of 2 over k raised to the 10th power um, is actually, well, that's just going to turn into cosine of 0. Because we had cosine of 2 over k raised to the 10th, that's just going to be cosine of 0 because we've established that as we plug in numbers into it until infinity, if we plug in infinity into our k expression, then the expression is going to go to 0, so we're going to have cosine of 0. And as we know, cosine of 0, well, that equals 1. Oops. Cosine of 0 equals 1. So what that means is I'm gonna write a therefore statement right here. Therefore the limit as k approaches infinity for a sub k, well, that's gonna equal 1. And 1 does not equal 0. And that would mean that by the divergence test that the series diverges because the terms do not go to 0. Since 1 does not equal 0, the terms do not go to 0, and therefore the series diverges. Let's see. So we have the series from k equals 1 to infinity of the rational expression, with the numerator being k raised to the 20th power, and the denominator being 20 raised to the power of k. And we want to know, does it converge? Does this series converge? Um, how can we tell that it converges, or how can we tell if it converges or not? The ratio test is a test that we can use in order to tell if a series converges or not. Um, and one of the indicators of why we should use the ratio test is because we have a power of k on top, and we have an exponential of we have k being raised to the power of 20 on the top, and then on the bottom we have 20 being raised to the power of k on the bottom, right? And that sort of indicates to us that we want to use the ratio test. And the ratio test has a formula that can be written like this, or a theorem, if you will, that can be written like this. All right, so R equals the limit as k approaches infinity for the absolute value of a sub k plus 1 over a sub k, and that's if R equals less than 1, if R is something that's less than 1, then the series converges. Well, what we need to do here is we need to determine like what is a sub k going to be and what is a sub k plus 1 going to be, because that way we can actually plug it into our formula for the ratio test. Um, so we'll say that we'll let a sub k equal, we'll say that a sub k equals what we have here. So that's just going to be k raised to the 20th power over 20 raised to the power of k. Okay, so then a sub k plus 1, a sub k plus 1, well, so we have to figure out what we're going to set that to. So this like really tripped me up before, but I hope I can explain it to like you guys in a way that you guys can understand, is because it's actually like once you see it, it's like, oh, it's kind of like that. So um, here we have k raised to the 20th power. So everywhere that you see a k, you're just going to put a plus 1. So k raised to the power of 20, okay, well, this is not a sub k, this is a sub k plus 1. So we're actually going to say k plus 1 raised to the 20th power. And then where there's a k right down here, so 20 raised to the power of k, no, actually it's going to be 20 raised to the power of k plus 1. You see what I mean? So then it's like, oh, okay, so everywhere that there's a k, we're actually going to put k plus 1, and that's what makes it a sub k plus 1. So that said, let's go ahead and we're going to set up our ratio. Right, so we're just going to follow this here. We're just going to follow this here. We're not going to worry about the limit at this point in time. We're just going to work with what's between these absolute value brackets. So, just for clarity, a sub k plus 1 over a sub k. And well, I don't know if I have room here. Let me see here. Probably try to put it a little bit lower. Um, well, a sub k plus 1, it's well, we know what a sub k plus 1 is here because we've already set it. So it's going to be k plus 1, k plus 1 raised to the power of 20 over 20 raised to the power of k plus 1. Okay, and then for a sub k, we already set a sub k equaling k raised to the power of 20 over 20 raised to the power of k. So we'll just go ahead and put that in the denominator. And we are dealing with a complex fraction, which we will address in a minute. We'll address this complex fraction. We're just going to reciprocate. So I think that the reciprocation is going to go like this. We have k plus 1 raised to the power of 20 over 20 raised to the power of k plus 1 times 20 raised to the power of k over k raised to the power of 20. All right. Now, the thing is here is like I can write this as one fraction. I think this is how you're supposed to do it. Um, so let's just write it like as one fraction. And we're just gonna put it all in the same fraction. And we can do that, right? This is multiplication of fractions, so we're just gonna go ahead and put it into one fraction. But then now it's like we need to regroup it we need to regroup everything so like that the powers of 20s are on one side, and then that the powers of k's and k plus well the power of k and the k plus 1 is on another side. So um you could say like we're going to regroup it in terms of fractions that have like exponents. So remember like when you had like terms, these are like exponents. And so let me just maybe if I just write it out, it will be easier to see. K plus 1 raised to the power of 20, and then we have k plus 1 raised to the power of 20, and then we're going to grab that k raised to the power of 20 because it's a like exponent, right? They're both being raised to the power of 20. And we're just going to split the fraction back up because, um, well, because we're going to. And so then we're going to have 20 raised to the power of k, 20 raised to the power of k, and then like exponents 20 raised to the power of k plus 1. Okay, so now we need to like simplify. We have to simplify, and well, how about we simplify in blue? Actually, this blue doesn't really contrast that nicely with the darker background, so how about we'll do this sort of blue? Personally, I like darker blue, but just due to the nature of the background, we're going to use this lighter blue. I like the darker background. It's easier on the eyes, I feel. So, so let's simplify, right? We got k plus 1 raised to the power of 20 over k raised to the power of 20. Um, and now that's going to equal, well, that we could just, and so we could just raise the whole thing to the power of 20. So we'll have k plus 1 over k, and then they're just going to raise this whole thing to the power of 20, right? And then this over here, well, we'll have 20 raised to the power of k over 20 raised to the power of k plus 1, right? But then this is going to require like a law of exponents, and so it's going to be like if I have a raised to the power of m, and then it's going to be like a raised to the power of n. So like in this case, m is k, and then k plus 1 is n. Well, that's going to be a raised to the power of m minus n. Okay, and we're just going to box this up just because we're going to use this rule, this logic, but we're not using these variables, so it's in a box. Just keep it organized, keep it clean. Um, and this is, so now we're going to have 20, and it's going to be 20 raised to the power of k minus k minus n. Or is it k minus n, k plus n? But, but, the thing about this is like when we simplify the exponent, and I'm just going to draw like a little arrow going down here because, no, honestly, wait, uh, let me just take this whole thing and then I'm going to say this. When we simplify the exponent, right, we're going to have 20, right? So, but it's going to be k, and then we're going to distribute this negative sign to both terms in this binomial. So it's going to really be k minus 1. I don't know why I put an n there. Hold on, let me just, sorry guys, mistakes happen. K minus 1, but it's actually going to be k plus 1. So this is going to be, and we just plugged it in. So 20 raised to the power of k minus k plus 1. Then I'm going to grab this 20 raised to the power of k minus k minus 1, because this negative symbol gets distributed to this binomial, right? And then that's literally just going to be That's literally just going to be, well, that's just going to be 20 raised to the power of -1, which is the same thing as 1 over 20. Okay, so now, and I'm going to stop using blue here, um, because we've already simplified it, but we are going to reset up a sub k plus 1 over a sub k with our new simplified forms. All right, so um, we got the new a sub k plus 1, a sub k plus, no, excuse me, a sub k. And then we got our simplified forms, right? So um, our first simplified form is going to be, well, let's just, honestly, this is we're just going to do the 1 over 20. So we just got that times what we had originally found first. We did this one first, so it's going to actually be um, uh, k plus 1 over k raised to the power of 20. Okay? And so, I don't know if we can really tell if that's okay or not. All right, I think, right? Yeah. And and um and now so there's a little something that's going on with this here. And let's address that with this nice purple color. Um so let's just sort of go off on our little simplification journey here when it comes to this rational expression raised to the 20th power. When it comes to k plus 1 over k raised to the 20th power, the reality of the situation is that um well we can actually split this fraction to make it k over k plus 1 over k, and this is going to be raised to the 20th. Okay, but then with that, one can imagine that it's actually the same thing as 1, as k over k is a form of 1. And so I'm pretty sure you could actually write it like this. Um, and and with that, um, that would mean that we can actually multiply 1 over 20 times 1 plus 1 plus 1 over k raised to the 20th. Okay. And so now we've just evaluated the, well, we evaluated the absolute value via the ratio test. Um, so even just to simplify this more, it is positive, but even if it wasn't, like if this did yield a negative, which it didn't, we would just take the absolute value of it and it would just be positive, but we don't even have to worry about that because it's not negative. So what we'll do at this point is we're going to take the limit of it. So we're going to grab this that we just found, this little pseudo answer here, and we're going to take the limit of it. So the limit as k approaches infinity, I cannot draw brackets today, you guys. 1 over 20, 1 plus 1 over k, and then so that's gonna actually be raised to the power of 20, and then let's finish off the brackets there. Okay, so like so the thing about this is that like since if you have uh if you have if you so as k approaches infinity for 1 over k, if you plug in 1 over 1, it's going to be 1. So we're going to plug in infinity for where the k is. 1 over 1 is 1. Okay. Then 1 over 2 was 1 half. Then 1 over 3, it's the numbers are going to start to get smaller and smaller. Then you have like 1 over 4, 1 over 5. As you divide 1 by bigger numbers, the result is going to get smaller. Well, and eventually it's just going to go to 0. It's just going to go to 0. So as k approaches infinity, 1 over k approaches 0. All right? So that means that 1 over k, it's just going to approach 0. So really what we're going to have is we're going to have the limit of k up as k approaches infinity of um 1 over 20 times 1, we're going to be adding 0, and then we'll raise this to the power of 20. Then that's actually, and so um well, now let's see. 20 1 plus 0 is 1, and then 1 raised to the power of 20, well, that's just going to be 1, and then 1 times 1 over 20, that's just going to be 1 over 20. Okay, so the limit as k approaches infinity is going to equal 1 over 20. But then before, remember, we said that this whole expression, this is going to equal r, the ratio. So that means that 1 over 20 equals r, the ratio. And so um, let's look at our constraints here. If r is less than 1, then the series converges. Well, so 1 over 20, so that's going to be less than 1. So that's good. Well, I mean, it's not really good or bad inherently, but that's good for if we want to see if the series converges or not. Well, that's good for this test. Well, okay, it doesn't mean that it's good that it converges. Let me just chill. Let me chill. What I mean is that the series converges because this checks out. Let's imagine, well, what's in front of us, so we don't have to imagine. We have this sequence of a sub k equals k plus 3 over k raised to the power of 2k. Well, what we should do is we'll go ahead and we'll just take the limit of this as it approaches infinity. The first thing that we can do, well, this is going to give us an indeterminate form. This is going to give us an indeterminate form because infinity over infinity raised to the power of infinity. So why don't we um why don't we manipulate this algebraically? So the limit as k approaches infinity of k plus 3 over k, and then we'll divide this by k because k is only being raised to the degree of 1. So we're going to divide it by k, or multiply it by 1 over k, and then raise this to the power of 2k. Can't forget that. And so this is going to give us give us the limit of the limit as k approaches infinity of, oh, let me see here. How does this go? I think it goes like k over k plus 3 over k, I think, over k over k. And this is going to be raised to the power of 2 times k. 2 times k, I think. And then, and so then from there, we'll say that the limit as k approaches infinity, there's a couple of forms of ones here. So this is just gonna be over 1, so we're just gonna like ignore that. And so we'll have 1 plus 3 over k, and then raise this to the power of 2k. So we have 1 plus, we have the limit as k approaches infinity of 1 plus 3 over k raised to the power of 2k. And then, as we know, as if we plug in infinity for k, this is just going to get really, really small. And so it's just going to become 0. And so what that means is that we're actually going to have the limit of as k approaches infinity of of 1 plus 0, I think. And that's going to be raised to the power of 2 times k. That does not look like a k. Wow, it's so pretty. Okay, that's 2k. And so that's really just going to be the limit of k um the limit as k approaches infinity for 1 raised to the power of 2 times k, right? Um but that just gives us an indeterminate form. Like we're going to have 1 raised to the power of infinity. Sorry, I'm very particular sometimes. Anyway, um, I think what we should do is let's put this in terms of x. Um, nothing against k, nothing against k, but I think we need to put this in terms of x. So f of x, and everywhere that there was a k, everywhere that there was a k, like up here, we're just gonna put an x. We're just gonna put an x, and so it's gonna be f of x equals x plus 3 over x raised to the power of 2x, and then so we'll say that f of k, f of k equals a sub k for all k being greater than or equal to 1. Well, so then we'll just take the limit. Of course, now we're working with x, so we'll have x, the limit of x as it approaches infinity for x plus 3 over x raised to the power of 2x. And and this is still going to give us an indeterminate form, but we will address that, and we will address it using what's called the logarithm technique. So it involves taking the natural logarithm of an indeterminate form. So for example, like well, this is the example. Um, so this is going to be the limit as x approaches infinity um of ln, so the natural logarithm of literally what we just had, of what we have was x plus 3 over x, and so but this is going to be raised to the power of 2x, right? I think. And then um and the reason that we do this is because there's a power rule that comes with that comes um with logarithms. So let me just write out that power rule really quickly. So if we have like a oh, and I'll just write it out right here since there's some space here. The natural logarithm of a raised to the power of b, and that's going to equal b times the natural logarithm of a. So that b is able to kind of just come right out front, and that is particularly useful in a problem here because here I don't really have that much room. So I'll just say like let me just try to squeeze it in here. We'll say that here a equals x plus 3. So I just want to be thorough. X plus 3 is going to be over x, and that's going to be what a is. And then b is going to be 2x. So what that means is that like um we can manipulate this, right? We can manipulate this because now this is going to become something that looks like this. So the limit as x approaches infinity of well, so do you remember how b is 2x and this is here? So b is right here. So now we're going to pull that 2x out front. Now we're going to pull that 2x out front, multiply it to the natural logarithm of a, which is x plus 3, I think. And um, so then, like, so now what we'll do is we'll simplify the fraction. Okay, so 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 in when it comes to simplifying the fraction, we're gonna kind of follow the same trend that we were doing before. So like 2x 2x times the natural logarithm of the split fraction x over x plus 3 over x. And then that's what that's going to look like. But of course, we could see that x over x is just a form of 1. And so this is going to be like the limit as x approaches infinity of 2x times the natural logarithm of 1 plus 3 over x, right? 3 over x. Um, and 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 we have the limit as x approaches infinity for 2x times the natural logarithm of 1 plus 3 over x. Okay, but we're going to look at this in two pieces. We're going to look at this in two separate pieces. So the first part, the first part, we want to look at what happens like so as 2x approaches infinity, right? And as x approaches infinity, but these guys are just going to turn into infinity. All right, and so like as for the second part, right, we'll have I think it's like the natural logarithm of 1 plus 3 over x. Well, if you plug in infinity for x, you'll find that this 3 over x is just going to go to 0. Okay, so we say 3 over x as x approaches infinity, this is just going to go to 0. Okay, so well, that's going to mean that we're going to have ln of 1 plus 0, and that's just going to be ln of 1, natural logarithm of 1, and the natural logarithm of 1 is 0. All right, so that means that that the product of 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 this, and let me just be clear, the limit as x approaches infinity of 2x times the natural logarithm of 1 plus 3x, and well, so that's going to give us a product, and the product is infinity times 0, and that is an indeterminate form. All right, that's an indeterminate form. So we want to make this a quotient, and the trick here is to replace the factor x with 1 over 1 over x, right? Because x equals 1 over 1 over x, okay? And that's because like, and I'll just write out like a little proof here. Um, well, if you have 1 and you divide it by 1 over x, okay, that's going to equal x, right? Because if you have 1 over 1 over x, and if you and then 1 over 1 over x, and then you reciprocate, Well, it's going to be x over 1, which is going to be 1 times x, and that's just going to be x, right? So the trick here is that we're going to replace x with 1 over x, because then that turns the product into a fraction. So that said, let me do a little side by side here. Quick side by side because yeah, like for me it helps to look at things side by side a lot of time. Um, because it just kind of helps trigger pattern recognition for me. So I want to write this out just as it was, 3 over x. Um, and then and so this is the same thing as the limit as x approaches infinity, um, of of uh, let's see, 2x times the natural logarithm. No, wait. 2, I'm going to remove that x, actually. I'm going to do 2 times the natural logarithm of 1 plus 3 over x. All right. And honestly, I'm going to stick a parenthesis here because I'm going to have an x on the outside of that, and within the bracket still, though. And so now, I could say that this equals the limit as x approaches infinity. Um, oh yeah, okay. 2 times the natural logarithm of 1 plus 3 over x. Um, and we're just going to close that off. We're going to close that off because right here, this is where we write out our x in a different form. But it still means the same thing, which we have proved over here. So now, what this is actually going to become is it's going to become the limit as x approaches infinity of I think it's like, we'll put this in a rational expression, 2 times the natural logarithm of 1 plus 3 over x, 3 over x, right? Over 1 over x. And now if you plug in infinity everywhere where the x is, the result of this is going to be 0 over 0, which is an indeterminate form where we can apply L'Hopital's rule. We're going to run that L'Hopital's rule. So we're going to have to differentiate the numerator and the denominator. So the first thing that we're going to do is, usually I like to take the derivative of the numerator first, but the derivative of the denominator is far easier than the derivative of the numerator. So we're going to do the derivative of 1 over x, which is the same thing as the derivative of x to the negative first power. And then that's just going to be a power rule. That's just going to be a power rule here. So, uh, let me say this is going to be the derivative of x raised to the power of n equals, I think it goes like n times x raised to the power of, what is it, n minus 1? Yeah, I think. And then, and then, um, and then so that's, and so then what that's going to give us is we're going to bring that negative 1 out front, negative x, and then might subtract 1 from a negative 1 is just going to be negative 2. And then we don't want a negative exponent, right? So actually, wait, hold on. So this is going to be a negative fraction, 1 over x squared, I think. Now, as for the denominator, um, well, we have the denominator. So as for the numerator is what I meant. So this is the derivative of the numerator. And then we'll get started with the denominator over here. Uh, okay, so I think what we have to do first is to take the derivative of the denominator. Um, I'm gonna draw an arrow to indicate that we're actually gonna do this over here because if we do the derivative of the denominator, it's gonna be like d over dx. 2 times the natural logarithm of 1 plus 3 over x. And then I'm going to factor out that 2. And so this is actually going to be 2 times the derivative of the natural logarithm of 1 plus 3 over x, right? I think. And then we need to use the chain rule for this. So, um, well, we'll say we could use a different orientation for the chain rule, just for funsies. Um, if y equals f of g of x, a composite function, well then dy over dx is going to equal f prime of g of x times g prime of x, because we have to differentiate the outside and then leave the inside alone, but then multiply by the derivative of the inside. So another way to look at this could be dy over dx equals dy over du times du over dx. And so that's going to give us the exact same thing. Well, that's the exact same thing, but it gives the inside function a name, which is going to be u in this case. All right, so let's get started with taking the derivative via the chain rule. So um, if u is g of x, then y is f of u, right? And then honestly we could just compare, right? Like we could say like that that uh that d of u, or excuse me, dy over du, it's the derivative, say derivative of the outside part. And then um you could say like that there, but then du over dx is the derivative of the inside part. Inside part. Okay? And so that would mean that dy over du times du over dx is the exact same thing, right? As oh man, I'm running out of room. Okay, wait. But this is important. This is important. So I'm going to say that dy over du times du over dx is the exact same thing as f prime of g of x times the derivative of g of x, right? Um, And so we can look at this with our example where we have um, where we have y equals the natural logarithm of 1 plus 3 over x, and uh, and then that would mean that the inside function, right? The inside function here would say the inside function is going to be u. The inside function is u, and that's going to be set to 1 plus 3 over x, right? But then the outside function is going to be f of u, because we've given u a name, right? And then f of u, it's going to be, so it's going to be ln of u, okay? And then the chain rule states that dy over dx is going to equal f prime of u, and that's going to be multiplied by du over dx. Okay, and f of u is ln of u, and then that would say, so that would mean that f prime of u is going to equal it's well that's going to equal um 1 over u, right? And then um oh man, I don't have any room. Wait, not good, not good. Hold on. Let me just write really, really small. Okay, so anyway, I'm just gonna work with what I got. Like, I'm just gonna figure this out. Like, I'm just gonna do it. Like, I don't care. Like, nothing will stop me. So then it's gonna be 1 over u. Um, and so then that would mean that, and we'll just do this over here, that du over dx equals d over dx, right? And the d over dx, so the derivative of 1 plus 3 over x, and that's going to equal negative 3 over x squared. Okay, so then dy over dx is going to equal 1 over u, and that's going to be multiplied to um 3 over x squared. And uh and so and then we can replace u with 1 plus 3 over x. And so that's going to be dy over dx equals 1 over 1 plus 3 over x. And and this is going to be negative 3 over x squared. Okay? And so that's going to be our answer. This is our answer for the derivative of the denominator. So, um, well, we don't really have that much room, but I just remembered that technically speaking, we need to multiply back that 2, right? Because remember when we factored out that, oh yeah, right here. Remember when we factored out that 2, like right here? So we need to multiply that back. So to multiply that back, we're going to have 2 times 1 over 1 plus 3x, and oh yeah, and then that's going to be multiplied to 1 just negative 3 over x squared. All right, guys, I don't think there's any way to get around this. I think I need more room. Um, I have an idea. Um, where's our numerator? Oh yeah. So this right here, this is the derivative for the numerator, and this is here is the derivative for the denominator. So now, what we'll have to do here is, well, we'll write in for L'Hopital. We'll write in for L'Hopital's rule. So we're gonna do 2 times, um, we'll do 2 times, um, 1 plus 3 over x. Okay. No, you know what? Actually, hold on, wait. I don't like the way that looks. Here. Because I'm already knowing that we're gonna need more room. So 2 times 1 over 1 plus 3x. Okay, the derivative of the numerator. And then we can't forget that we do have this negative 3 over x squared. Okay, but all of this is actually going to be over 1 over x squared because that's what we got for the derivative for the denominator. Now, uh, I want to rearrange this. I want to I I want to rearrange this. And there's a rule. There's a rule in algebra. Um, so if I do like delta times lambda times phi over c. Now that's the same thing as uh, delta times lambda times phi over c, right? This is the formula, okay? Or if this is a little bit too much extra, I could say a times b times c over d equals a times b times um c over d. You can write it either way you want. I just figured I should, I don't know. I like to have fun with my notes. All right, I like that. I like to, be creative, but it's the same thing. I'm gonna roll with the Greek formula. So I'm gonna say that uh delta equals 2, lambda equals 1 over 1 plus 3 over x. Okay, and then psi, and let me just do a bullet point here. Psi equals um negative 3 over x squared, and so phi equals negative 3 over x, excuse me, phi equals negative 3 over x squared, and psi, well, that equals negative 1 over x squared. All right. So then applying this into our formula, we could find that we could find that well, it's going to be I don't know, should I do a side by side? I feel like I don't have to because it's right underneath. So we're gonna have 2 times 1 over 1 plus 3 over x times the complex fraction of, on the top we're gonna have 3 over x squared, okay? And then on the bottom we're gonna have 1 over x squared. So we got negative 3 over x squared, and then on the bottom we have, so on the top we have negative 3 over x squared, on the bottom we have negative 1 over x squared. Okay? And just note that all I did was I just plugged that into our formula, all right? That's all I did. Um, and so the simplification of this is it's gonna be like um, let's see, well, we're gonna reciprocate. So we'll have 2 over 1 plus 3 over x, right? And then this is gonna be times negative 3x squared, yeah, negative 3x squared minus, oh, excuse me, negative 3x squared over 1, excuse me, negative 3 over x squared over negative 1 over x squared. And then there's going to be some cancellation. There's going to be some cancellation here. Well, these x's are going to cancel out, and these negatives are going to cancel out. And so what we're actually going to have is 2 over 1 plus 3 over x times 3. All right. And then that's going to equal, well, that's going to equal, 2 times 3 is 6 over 1 plus 3 over x in the denominator. And then we're going to go ahead and we're going to plug that into our limit, which is going to be the limit as x approaches infinity of our what we have found, which is going to be 6 over 1 plus 3 over x. And so then if you plug in infinity into x, well, this is actually just going to go to 0, right? Because as you plug in larger numbers for x, you're going to divide 3 by larger numbers, and it's just going to get smaller and smaller. It's going to go to 0. So we're going to have 6 over 1 plus 0, which is just going to be 6, right? But since we took the natural logarithm at the beginning, which we can't see anymore because we didn't have enough room, but since we took the natural logarithm at the beginning, right, the log technique that we talked about, remember, um, that means that we have to exponentiate. So the answer is actually going to be e raised to the power of 6, and that's going to be the answer because we did the log technique and we need to exponentiate and bring that back, or else it's not going to balance it out. So in conclusion, the limit as x approaches infinity for x plus 3 over x, which was our sequence, raised to the power of 2x equals e raised to the 6th power. And then that's going to be our answer. Let's do another one, shall we? So here we'll have the series of, well, instead of using k, how about we use n, right? We'll switch it up a bit. Um, This is the index, by the way. This is called the index. It's usually people will use like n or k, but today we'll use both. So we'll have n. It starts at 1, and we're going to infinity, and then so for this series, it's going to be in the numerator the square root of n, and then in the denominator we're going to have n raised to the power of 2 plus 3, and um and so. And so here we want to see if the series converges or not. And um, to do that, just want to be clear, well, we're going to use a comparison test. So if 0 is less than or equal to a sub k, and a sub k is less than or equal to b sub k, and um, and if the series of I think it's if the series of B sub k converges, if the series of B sub k converges, then 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 the series of A sub k, well, the series of A sub k also converges, such that such that the that A sub k is less than or equal to B sub k. This is a fraction with powers um, of n, and and that means that n has an exponent. So n has an exponent here, and n technically has an exponent here. It's raised up. It's the power of 1/2. So here we see that the powers of n are 1/2 and 2. So that means that we're going to compare it to what is called a p-series, and a p-series is of the form. It's a series of the form 1 over, I think it's 1 over n raised to a power. However, um, the power, it has to be, if the power if the power is greater than 1, then the series converges. All right. So if you have a series 1 over n raised to the power of p, such that p is greater than 1, then the series converges. And 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 um and because we have powers of n, one being 1 over 2 and the other one being 2, we're going to compare it to the p-series. Um, so we're going to start off by looking at the main behavior of the square root of n over n squared plus 3. So like like, let's investigate, like, what's even going on, right? What's going on? Well, um so like for a very large n, if you put like a really large number for n, the plus 3 in the denominator, like right here, let's look at the denominator. Put a very large number for n, the plus 3, it's negligible. Like, the larger n is, the smaller 3 is in juxtaposition with it, because the plus 3, it's small when compared to n raised to the second power. So we're just going to think of this, we're just going to approximate it, and we're just going to say that this is the square root of n over n squared. We're just going to neglect that 3, okay? So what we'll do now is we're going to simplify, all right? This, as we've established, is the square root of n is going to be n raised to the power of 1/2 over n squared, okay? And and then by the laws of exponents, we could say that n raised to the power of 1/2, well, we could bring this up, this n squared up, such that we subtract 2 from this 1/2, all right? And with a little bit of algebra, um, well, we're going to have n 1 over 2 minus, well, this is really 2 over 1, so if we do 4 over 2, so we have common denominators, this is just going to come out to be, um, this is going to be negative 1 over, no, excuse me, this is going to be negative 3 over 2. And then we want to get rid of that negative sign, we'll just put it in the denominator then. So it's going to be 1 over n raised to the power of 3 over 2. And and so we can we can rewrite this. So now our series, it will look like this, right? We can compare it to this series. So we'll have, we got n over, no, n equals 1 infinity, and we got 1 over n raised to the 3/2 power, which of course this is, we could rewrite this as, well, we could write this so n equals 1, you got the infinity, and then this is 1 over 3, and we could even put this like as a decimal, so like 1.5, right? And um and so then we can use the p-series rule, right? Says that we say that if p-series has the, we know that p-series has the form of 1 over n raised to the power p, and it converges that if p is greater than 1. Now here, for us, right? For us, we'll say that p equals 3/2, or if you'd like, 1.5. And since 1.5 is greater than 1, the series, um, that would mean that the series, it converges, right? So like, let's just like sort of get our bearings straight here. We have n equals 1, the series of n equals 1 to infinity of the square root of n. This is our original problem here. N squared plus 3. Okay? And we are comparing it to our series n equals 1 to infinity, of 1 over n raised to the power of 1.5. Okay? Now, um, at this point, let's kind of just like let's start with the denominator. Let's just like analyze the denominator, right? For every positive n, for every positive n, for every positive n, here's n, um, n squared is going to be greater than, no, wait, hold on, I'm sorry. N squared plus 3, because we're looking at the denominator here. N squared plus 3, it's going to be greater than n squared, right? Because you have that plus 3. That plus 3 makes it larger. So like, for an example, right? Like, we could just like go ahead and run an example. Um, any number, we'll say we could plug in 5. No, let's not do 5. Let's do 3. 3 squared plus 3, um, 3 squared. So 3 squared plus 3 is greater than 3 squared, right? Yes, because that's going to equal, um, that's 9, no, 9 plus 3, and that's going to be 12 is greater than 9, right? This is a correct mathematical statement. And the bigger denominator means the smaller fraction, okay? Bigger denominator, smaller fraction. So, for an example, right? Uh, we have, um, if you say like 1 over 12, 1 over 12, it's going to be less than 1 over 9. And because 12 is the bigger denominator here, we can draw a comparison to what we have going on and say that, um, well, let's see, the square root of n over n raised to the third power plus 3, it's going to be less than the square root of n over n squared. And so the top stayed the same, and only the denominator changed. And we can simplify the right side of the equation. And well, if we simplify the right side of the equation, okay, it's going to be the same thing as n raised to the 1/2 power over n squared. And then we've done the arithmetic up here, or I guess not arithmetic because arithmetic implies the absence of variables. So we'll do the math. We'll do the subtraction. We'll find the difference between 1/2 and 2, and that's just going to be, this is going to simplify to be, when we did it before, -3/2. Okay? And the negative exponent, right? That means that we're gonna move it to the denominator. So n raised to the power of 3/2 in the denominator. Okay? So at this point, our statement it can be written as follows. The square root of n over n squared plus 3 is less than 1 over n raised to the power of 1.5, which is just another orientation of 3/2. So, um, now we know, right, that the series we know that the series we know that the series um of 1 over n raised to the power of 1.5, well, we know that this converges. And we know that this converges because it's a p-series such that p um, equals 1.5, which is in fact greater than 1. So by the comparison test, we are going to say that this series converges. I'm not going to even attempt to try to rewrite this out. I took this directly from Pearson Labs, so credit where it's due, credit to Pearson Labs. Um, it says to determine how many terms of the following convergent series must be summed in order to be sure that the remainder is less than 10 raised to the -3rd power in magnitude, and it's the infinite series starting at k equaling 1 to infinity of -1 raised to the power of k over k raised to the power of 5. And we're told already that this is conversion, so we already know that it's conversion. We just want to make sure that the remainder is less than 10 raised to the -3rd power in magnitude. And from looking at this, we can tell that this is an alternating series. This is an alternating series because what gives this away? Oh, hold on. There we go. Because what gives that away is that if there's a -1 involved. Now, that's not always going to be the case, but in this case, it just happens to be an alternating series. But more often than not, with these sorts of problems, in my experience at least, I've found that if there is a negative in there, then it's probably going to be an alternating series, but that's not like a clear cut, like cookie cutter, like always going to be. That's not that logic. You can't always apply it, but here we can. Luckily, of course, this is curated. So we're going to say this is an alternating series, and that -1 gives it away to us. Now, um, there is an alternating series error bound. Error bound. And it's written as followed. It's +1. The absolute value of r sub n is going to be less than or equal to a sub n plus 1. All right. Now, here we need to determine like what's a sub k? What is a sub k? Well, here a sub k a sub k, well that's going to equal 1 over 5, no, 1 over k raised to the 5th power. And we need to make sure that the remainder is less than 10 raised to the -3rd power. So you got 10 raised to the -3rd. And then well, if you have like a 10, right? 10.0, 1, 2, 3. So we're moving to the left, and then you're gonna have like 1 and 2 like that. and so then you could say that 10 raised to the negative third is the same thing as 0.001, and the requirement is of such that 10 raised to the negative third, um it's going to be greater than a sub n plus 1, right? And just note that we're trying to find how many terms are needed so that the terms are less than 10 raised to the power of negative 3. And for an alternating series, the error, it's no bigger than the next unused term. And here, a sub k equals 1 over k raised to the fifth power. And that means that the next unused term defined as a sub n plus k, the neglected term, as some might call it. Wait, no, wait. The next unused term, the next neglected term, a sub n plus 1, plus 1, and that's going to equal 1 over n plus 1 raised to the fifth. This is the next unused term, the next neglected term. All right. And when and we want the error to be less than 10 raised to the negative third power. So that means that that we require that 1 over n plus 1 raised to the fifth. Well, that's going to be less than 10 raised to the negative third. Sorry, I'm just checking my work. Um, so another way that we can write, another way that we could write 10, um, 10 raised to the negative third is 1 over 1,000. And then this is going to become 1 over n plus 1 raised to the fifth. That's going to be less than 1 over 1,000. And we are going to compare the denominators. We're going to compare the denominators here because the thing is that if you have two fractions and both have a numerator 1 and the fraction, then that and they both have the numerator being 1, then the fraction that has the bigger denominator is going to be smaller. So like for an example of this, like an example of this would be like 1 over 25 is going to be less than 1/5 because it has a bigger denominator. That's why 1 over 25 is going to be less than 1 over 5 because the 25 is bigger than 5. Okay? So then in our case, right, when we have 1 over n plus 1 raised to the power of 5, um, less than 1 over, which is less than 1 over 1,000, that means that by convention, that n plus 1 raised to the fifth power, that must be bigger than 1,000. Anyway, so we have 1 over n plus 1 raised to the fifth power is less than 1 over 1,000. And we want to solve this for n. We want to solve this inequality for n. So that means that we need to isolate this n, and we're going to start by bringing it up from the denominator. Okay, so we'll multiply both sides of the inequality by n plus 1 raised to the fifth power. And then this is going to cancel here. The n plus 1 raised to the fifth is going to cancel on this side. And we will have, I don't think I have room here, so we'll do it over here. we'll have 1 is less than, well then, so that's actually going to be n plus 1 raised to the fifth over 1,000. And then now we're going to multiply both sides of the equation by 1,000, I think, so we can isolate that. So 1,000 times 1, and then n plus 1 raised to the fifth power over 1,000 times 1,000. And then that's actually going to be 1,000. Sorry, my cat's, she's looking out the window and making noises. 1,000 is less than n plus 1 raised to the fifth power. At this point, we have 1,000 is less than n plus 1 raised to the fifth power, okay? Which this is quite literally the same thing as, I'm going to use some chemistry notation here. This is not standard mathematical notation, and again, neither are these arrows in this context. But go ahead and snag this from chemistry, right? And rewrite this as n plus 1 raised to the fifth is greater than 1,000. It means the exact same thing. Okay. We want to isolate that n, and we're going to do this by taking the fifth root of both sides of the equation. So just go ahead and copy it. N plus 1 raised to the fifth is greater than 1,000. Okay, then we're going to put a radical here with, oops, just be very clear. Put a radical here, all right, and with an index of 5. And this is the fifth root. Let me see here if I can make this a little bit neater. This is the fifth root, okay? And then these are going to cancel. This index is going to cancel with this exponent here, okay? And this is actually going to turn into n plus 1 is greater than the fifth root of 1,000. And um, well, if you take the fifth root 1,000, it's gonna, I'm gonna approximate it. It's like approximately 3.981 something something. I think it's 81. Actually, I don't want to say because I don't know 100%, but this is approximation, right? So it's gonna equal approximately 3.981 and then onward. And uh we are going to round up. We're going to round up to a whole number. We're going to round up to a whole number. So the number that we're going to round up to is going to be 4. 3.9, let's just say that's 4. Okay. That means that n plus 1 equals 4. And then we're just going to subtract 1 from both sides. Okay. And then that's going to mean that n equals 3. Okay. So we were originally asked how many terms are going to need to be summed in order to make sure that the remainder is less than it's going to be less than 10 raised to the power of negative 3. Well, the answer to that is we're going to need 3 terms. 3 terms. All right, so we have a series, and it's going from, let's start at k equals 1 to infinity. And, well, it's going to be 1 plus 1 over k. And well, this is going to be raised to the power of k, which is also raised to the power of 2. We want to understand, like, is this going to converge? You know, like, is this going to converge? Is it going to diverge? How do we test for this? Like, is it going to converge? Is it going to diverge? Like, how are we going to test for this? Well, the root test is useful when the whole entire term is being raised to a power that involves k. Um, when everything is being raised, when the whole term, excuse me, when the whole term is being raised to the power of k, well, then the kth root can cancel one factor from the exponent. And so let me show you what I'm talking about. So this is called the root test. Say we have like an infinite series. So like let this be an infinite series. The infinite series of a sub k, and that's an infinite series. And then we'll let let's see, rho equals the limit as k approaches infinity. As k approaches infinity, um, for the this is a radical with the kth root, with the kth excuse me, we'll say an index of k for the absolute value of a sub k, the absolute value of a sub k. And now, and if, right, if rho is greater than 1, no, wait, excuse me, I'm sorry. I will say if rho is less than 1, we will address it with if rho is greater than 1. But first, if rho is less than 1, then we'll say absolutely convergent. And absolutely convergent, therefore it converges, right? Um, if rho is greater than 1, and this here will include infinity. So we'll say this includes rho equaling infinity. Then uh, the series diverges. And lastly, if rho equals 1, that would mean that this is inconclusive. The root test is it's useful with powers of k when everything in the a sub k is being raised to the power, I guess, when all of the terms are being raised to the power of k. All right. That said, we've got a sub k here. Well, a sub k equals 1 plus 1 over k raised to the power of k raised to the power of 2. And with this, we're just gonna go ahead and set up the root test. Um, that is rho is equal to the limit as k approaches infinity of the kth root of a sub k, which is 1 plus 1 over k raised to the power of k raised to the power of 2. All right. Now, a kth root means the power of 1 over k. So like I was like before I was like, well, what is a kth root? Like what does that mean? What does that even mean? Like kth root? It's means means power of 1 over k. And then so what we can actually do here is utilize when we were evaluating this expression here is we could utilize the one of the power rules. That is the power rule of, I don't know if I have enough room here. I could say a raised to the power of m raised to the power of n equals a raised to the power of m times n. And so then what that's going to mean is we could take our expression here, 1 plus 1 over k, and we're going to raise it to the power of k, raise to the power of 2, and we're just going to go ahead and raise this to the power of 1 over k. And then we'll utilize our power rule to go ahead and transform this into 1 plus 1 over k, and this is being raised to a power of k that's being raised to the power of 2 times 1 over k. All right? And just to be clear, this is this here is in the exponents place. And um and so what that will turn into is 1 plus 1 over k raised to the power of k squared over k. All right? But then this is only being raised to the first power. This k is only being raised to the first power, so we're gonna have a cancel. We're gonna have a cancel. All right, and so then that's gonna mean that 1 plus 1 over k is being raised to the power of k because there was two k's. This is being raised to the power. This is the second degree. This is the first degree, and so there's still gonna be one left over in the numerator of this exponential power. So we're gonna have 1 plus 1 over k raised to the power of k. At this point, we're going to use the E limit formula. Are we going to use the E limit formula? I think we're gonna actually, yeah, because look at it. The E limit formula. The limit, right? I think. Hold on. You guys, I don't know what I'm doing. No, I was kidding. I do. I have an idea. I mean, I'm not like 100% sure, but like I'm pretty sure. Let's see. K the limit as k approaches infinity of, this is the E limit formula that I'm writing out, by the way, of 1 plus 1 over k. Remember before we had like we were using an n, or no, we were using an x. No, we were using an x, I think. But we got 1 plus 1 over k raised to the power of k equals Euler's number. That literally is what we have, right? There's not much else that we need to do. That's literally what we have. So that means that this here, 1 plus 1 over k raised to the power of k equals Euler's number. And that means that Euler's number equals rho. And and um and E, by definition, well, it goes on forever. What's a decimal that goes on forever? But it's equal to what? I think it's like 2.718. I made up a song about it. Um, 100 likes, I'll share the song. 71828 and so on, because it doesn't, we don't, the rest of these is sort of like it's not arbitrary, but it's not really relevant to us because we already have this. We want to look at this 2 here, this 2 before the decimal place, because that means that E is greater than 1. Okay? And E is rho. And if rho is greater than 1, if rho is greater than 1, that means that the series diverges. So what that means here is that the series diverges because of the fact that rho is equal to E and E is greater than 1. All right, so say we have a series, right? And it starts at k equals 1 and it goes all the way up to infinity. And in the series, we have -1 raised to the power of k plus 1 times the rational expression of the natural logarithm of k over k squared. And we're looking at this and we're like, well, does it converge? And it's an interesting question, honestly. I never really got into why this is interesting, because if it converges, that means it approaches a finite number. That means that if you add up literally all of the numbers to infinity, if you put every number, well, I guess starting at 1, and you plug 1 into this expression, right? Everywhere that there's a k, and then you take all of these and you do it, you get an answer, right, for 1, then you plug in 2, and then you get an answer for 2, and you plug in 3, and you keep going all the way up into infinity, and you add them up, you can literally calculate the number that it's going to sum to be. And that's huge. Like that, well, in some cases it's small. Okay, I'm sorry, dude. I'm actually such a nerd. It's just interesting. It's an interesting notion that you can literally take all of the numbers and then it goes to not only a finite number, but you can literally calculate it from 1 to infinity. I mean, infinity doesn't end. So the fact that you can figure if it converges or not, I mean, that's pretty cool. All right. So, um, so because there's a -1 here, I mean, there are cases where it's an alternating series when there's not a -1, right? But this -1 here, it gives away the fact um, that this is an alternating series. This is an alternating series, and this is an alternating series. And what that means is that it alternates. It's not like your car's alternator. It's an alternate. I gotta stop. Okay, it's like it the terms that when you sum them, they shift from being positive to negative. They oscillate between positive and negative. They interchange back and forth. It's positive, negative, or negative, positive, and whatnot. So let's just enumerate. So let's say that we plug into our function here. Um, we'll find the partial sum, call it. So um, if this is s sub n, right, then we're going to find s sub 1. And s sub 1, you could find s sub 1 by being like, okay, -1 raised to the power of 1 plus 1 times times um, the natural logarithm of 1, and that's going to be over 1 raised to the power of 2. Okay? And so if we calculate that, that's very interesting. So if you calculate that, that's actually going to be 0. And then we'll find s sub 2 by, well, we're going to do -1 times 2 plus 1 times the rational expression, the natural log in the numerator with a 2, and, well, it's going to be 2 raised to the power of 2. All right, and then if we run this calculation, okay, this is going to, I'm just going to do an approximation here. This is going to be -0.173. Okay, and then we're going to do, what did I say? This is actually, so this is s sub, and this is actually s sub 2. All right, then we're just gonna do s sub 3 just for good measure. And that's going to be -1 raised to the power of 3 plus 1 times the natural logarithm of 3 over 3 raised to the power of 2. And then I'm just gonna run this calculation. We're just gonna do just a small approximation. It's just gonna be 0.122. And yeah, yeah. And then I'm gonna just because I'm just gonna put s sub 4. So same sort of idea. You plug in a 4 everywhere where there's a k. Um, yeah, and so that's actually gonna be, we can approximate that to be um -0.086. So, and the reason that we want to enumerate like this is because the alternating series test, it needs to meet like these like certain constraints. And one of those constraints is that well, obviously the series needs to alternate, which it does because we have 0, okay? Then we have a negative number, then we have a positive number, then we have a negative number. So that checks out, it's alternating between positive and negative. Fine. But another constraint in order to apply the alternating series test is that the numbers need to get smaller. And as we can see, the numbers are getting smaller. They're decreasing in magnitude. The absolute value of them are decreasing in magnitude because you could argue, well, no, this is a mathematical fact that a negative number is smaller than a positive number, regardless of the digits. But if you were to take the absolute value of it, in other words, if you were to make this negative 0.173 positive, um, then it would be smaller than this 0.122 that's also positive, right? So we're looking at it, they need to be decreasing in magnitude no matter whether or not they're negative or positive. We're not looking at that. We're looking at the absolute value. Okay, it's distance from 0. Now, um, now that said, uh, the alternating series test, this is what it says. All right, so say you got a series. All right, okay, hold on, wait. So you got a series, right? And the series is -1 raised to the power of k times a sub k, right? And so the idea is that this converges um if and only if um if a sub k is eventually is if a sub k is decreasing in magnitude, right? The absolute value, it's decreasing in magnitude as you enumerate, um and and um and the limit as k approaches 0, the limit as k approaches 0 for a sub k equals 0. All right, then the series converges. Okay, so let's just check this out. Let's just check this out. So, well, the positive part of we need to separate the positive part from the negative part, right? So let's just grab the positive part. So the positive part, it's gonna be a sub k, and that's gonna be a sub k is equal to the natural logarithm of k over k squared. All right, and um, and so we want to check. Let's check, like, is a sub k? We want to check, is a sub k approaching 0? Is a sub k approaching 0? Um, because we need the limit. We need the limit as k approaches infinity of ln of k, the natural logarithm of k over k raised to the second power. All right. Well, the thing is that the denominator k squared grows much faster than the natural logarithm of k. All right, it grows exponentially. The denominator k squared grows faster than the natural logarithm of k. And so what that means is that what that means is because if you have the natural logarithm of k, okay, and the that's over k squared, due to the fact that the denominator k squared grows much faster than the natural logarithm of k, this is going to go to 0. Okay, so, and we can just sort of be very clear about this statement. The limit of k approaching, the limit as k approaches infinity for a sub k here, which we've defined a sub k, well, that's going to be 0. All right, that's going to be 0. And so we want to check, is a sub k decreasing? Um, we want to check if a sub k is decreasing for any large number k. Um, so a sub k, right, which equals a sub k, which equals the natural logarithm of k over k squared, decreases because k squared eventually it's going to grow much, 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 much more faster um than the natural logarithm of k. So a sub k is non-decreasing for k greater than some index n, right? So because the alternating series test says that the series of a negative 1 raised to the power of k of a sub k, it converges if a sub k is eventually decreasing, which it is, right? Um, and even like without, like, yeah, it oscillates between negative and positive, but like the numbers are decreasing. Like they are decreasing on both the positive and the negative side. This is decreasing. It's going to zero. And the limit as k approaches infinity of a sub k is also zero. We can say that this series converges. Let's do another one. This is going to be the series from k equaling 1 to infinity. And let's see, this is going to be a rational expression of k raised to the 7th power, with the denominator of k raised to the 9th power plus 7. All right. So this is a positive series, and well, I should be specific. We want to know, does it converge? Does it converge though? This is a positive series, and so we're going to use a comparison test to compare it to a simpler p series. Right? We spoke about the p series before a little bit, but let's start off by looking at the um let's start off by looking at what a sub k is. But really quickly, let me just state. Now let's analyze a sub k. So we have a fraction, right? The rational expression, it's k raised to the power of 7 over k raised to the power of 9 plus 7. Okay. And for any large k, the plus 7 is very small. It's a very small component when you put it in juxtaposition with the k raised to the ninth power, right? Um, so the the expression's behavior, it's mainly going to be dictated by k raised to the power of 7 and k raised to the power of 9. The 7 sort of in the denominator, the 7 here, it just kind of becomes negligible, right? Now we're looking at the powers. All right. So what we'll do is we will simplify um, as a k raised to the 7th power over k raised to the ninth power, and this is going to become um, 7 minus 9, and that's going to equal k to the negative second power, which we can put that in the denominator to get rid of that negative exponent. So it just gives me 1 over k raised to the second power. And and we're gonna and so we're gonna compare this with with um with the series k equaling 1 all the way up to infinity for 1 over k squared. All right, and we're going to use the p series rule. So over here, let's talk about the p series. Give ourselves a bit of a refresher on what that is, because because the p series, well, it looks like this. It's going to be uh, 1 over k raised to the power of p, and p is going to be greater than 1. P is going to be greater than 1, and if this is the case, if this is the case, then the p series, it converges. All right, so the p series has to have p greater than 1. Now here in ours, right, we have p equals 2, all right? here for us, p equals 2, and 2 is greater than 1. And and that means that this converges, that this series here converges. And so like let's just like look at the comparison. Let's just look at the comparison, and we're gonna start with the denominator here. So we'll do k raised to the power of 9 plus 7, and this is going to be greater than k raised to the power of 9, right? Because there's this one, they're both k's raised to the power of 9, but this one has a plus 7, and so it's always going to be bigger. And the denominator, if you were to make this like a fraction, right? We have k raised to the power of 9 plus 7, right? This is going to be less than, oh, I'm sorry, hold on. This statement is true. K raised to the power of 9 plus 7 is greater than k raised to the power of 9. Um, and the denominator, k raised to the power of 9 plus 7, it's bigger than k raised to the power of 9. In a bigger denominator, it means a smaller fraction, right? So if we have k raised to the power of 7 over k raised to the power of 9 plus 7, this is going to be less than k raised to the power of 7 over k raised to the power of 9, right? Because it's a bigger denominator, same numerator for both of them. So that said, we can draw the conclusion that k raised to the power of 7 over k raised to the power of 9 plus 7, well, that's going to be less than 1 over k squared. Okay, and so if we apply the comparison test, then we have 0 is less than k raised to the power of 7 over k raised to the power of 9, that's a 9, plus 7, all right, and that's going to be less than 1 over k squared, okay, and 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 we know that the series of 1 over k squared, we know that this converges. We know that this converges. So therefore, via the comparison test, this series here, right, this series as k set to 1 all the way up to the power, k equaling 1 all the way up to infinity for k raised to the 7th power over k raised to the 9th power plus 7, via the comparison test, this series converges. Let's have the sequence of a sub n equals ln of 2n over ln of n plus 1. And we'll have this for n equaling 2, 3, 4, 5, and so on. All right, so the series starts at 2. Excuse me, the sequence starts at 2. This is a sequence. This is a sequence here. This is a sequence. So the sequence starts at 2. Um, well, let's say we want to determine whether or not the sequence converges or diverges. Um, so in order to do this, we're going to take the limit. Let's see here. We're going to take the limit as n approaches infinity of our expression here, natural logarithm of 2 times n over the natural logarithm of 2, no, natural logarithm of n plus 1. Okay, so let's say we plug in infinity for n in this expression here. Well, 2 times infinity is infinity, and infinity, the natural logarithm of infinity is infinity. So we'll have an infinity in the numerator. Now as for the denominator, well, what's infinity plus 1? Infinity plus 1 is going to be infinity, and then the natural logarithm of infinity is infinity. And this is an indeterminate form. I think that's how you spell that, but at least I can say I tried. So, this is an indeterminate form, all right? Um, this is an indeterminate form for, let's see here, um, we'll say f of x. F of x equals ln of 2x over ln of x plus 1. And this is f of n f of n equals a sub n for all of well, we start at 2, so n being greater than or equal to 2. Okay. Um and so if um we want to take the limit of f of x, right? We just switched out that n for an x. Um, and so we want the limit as x approaches infinity for the natural logarithm of 2x over the natural logarithm of x plus 1. Well, we have to apply L'Hopital's rule. LH for an abbreviation. L'Hopital's rule. In other words, we need to take the derivative of the numerator and the derivative of the denominator. In order to take the derivative of the numerator, we need to apply the chain rule. And let me just write out the chain rule. And you might notice that um, these variables switch up a bit, right? I'm gonna be working with x variable here, and it doesn't. They're interchangeable, um, and so just note that the formation of where the placements of the variables that correspond with one another is the same, and that um, I could put f, I could put g, I could put x, I could put theta, I could put lambda, I could put c, but and I could use other letters of the English alphabet. It doesn't really matter. It's just the operations. It's the operations that it shows due to their placements next to each other and with the operators. So, um, let me not go off on a tangent here. We need to identify what f is and what g is because the chain rule says that we need to take the first we need to excuse me we need to differentiate the outer function and then multiply it by the derivative of the inner function, and we have to identify what f is and what g is for the natural logarithm of 2x. In other words, we need to identify what's the outer function and what's the inner function. So we're working on the numerator here. Numerator. This is the numerator. And we want to know what what's the outside function, what's the inside function. Um, well, well, we want to match, so we're trying to find y equals okay, sorry. We need to find um so y equals the natural logarithm of 2x, right? So we we're going to match that we need to match that to the chain rule form. The chain rule form where y is equal to um f of g of x. Okay. So the outside function, the outside function, the outside function, well, we can call that um we'll call that f of phi. All right, the outside function is f of phi, and and um and so that's going to be such that phi is a placeholder. It's interchangeable. It doesn't matter really what it is. It's just showing that like, we're going to put g of x inside of there. All right. So the inside, the inside function, the inside function, well, that's going to be g of x. All right. And that's the inner contents of what is inside of the natural log, what the function, the natural log of 2 of x. So g of x is going to be 2x. Now the chain rule, in order to, we need to find, the chain rule calls for us to take the derivatives of both of these functions, f prime of phi and g prime of x. So first we're going to find f of phi. All right. So well, we already know what f of phi is, but we're going to find f prime of phi. So of phi, f prime of phi, and well, since f of phi is the natural log, if we take the derivative of the natural logarithm, it's going to be 1 over phi. All right. That's the derivative. So then so what that means is that, so I'll do this over here. What that means is that f prime of g of x, f prime of g of x, oops, there should be a parentheses here. F prime of g of x equals 1 over g of x, right? Because that's where phi is. We're going to replace that with that. Um, and and uh, and so and g of x, we've assigned g of x is going to be the inner contents of the natural logarithm, so it's going to be 2x in the denominator here with a 1 up top. So then what we'll have to do is we're going to have to find like what's g prime of x, because we need that in order to, I usually do this with my formulas, my apologies. Um, we need to find like what's what's the derivative of g of x, g prime of x. So we can take the derivative of g prime of x in our heads because it's it's the derivative of 2x. The derivative of 2x, so if you factor out that 2, or you just apply the constant multiple rule for differentiation, it's going to be 2 times the derivative of x, and the derivative of a variable is going to be 1. So it's 2 times 1, and then the derivative of 2x is just going to be 2. All right. So we'll now we're going to multiply them together. Now we'll multiply them together. So the derivative of ln of 2x, well, that's going to be, I think that's going to be 1 over 2x. I think it's going to be 1 over 2x, and 1 over 2x times 2, right? Because it's the chain rule, and we need to differentiate the outer function and then multiply it by the derivative of the inner function, and that's exactly what we're doing. So that's what we have done here. And oh gosh, so that's going to be 2 over 2x, which is just going to be, I think this is just going to be 1 over x, right? I do believe that's just going to be 1 over x. So that's the numerator, okay? And then let's do the same for the denominator. Denominator. Because the denominator is also a composite function, and it's going to call for the chain rule. So the denominator here, it's going to be y equals ln of x plus 1. And again, we're trying to write this as as f as f of g of x, and so that would mean that we need to find the outside function, and um we need to find the outside function, and we need to find the inside function. So we'll do the function outside function, and we'll call that f of, oh, let's just pick a random variable psi. Okay, so um and so that's going to, we're going to set that to the natural logarithm of psi, again, an interchangeable variable, doesn't matter, just to show that this is going to be the contents of where we stick g of x in. And so, um, and so, so the inside function of this of what we have in the expression, the inside function, well, that's going to be g of x, okay, and then g of x equals x plus 1 because that's what we have on the inside of the natural logarithm. Now, we need to find f prime of psi, okay, and well, and so then uh, f prime of psi, so f prime of psi is it's going to be um so the derivative of the natural logarithm, it's going to be 1 over psi, okay, and um and so and so really, well, that's just going to be f prime of g of x, right? And then, well, that's going to be, we're going to, where psi is, we're going to put what we have for g of x, which is x plus 1, all underneath 1. Okay, so also, we need to find what the derivative, for this last part, we have to find what the derivative of g of x is. And this is, I do believe this is a linearity rule for differentiation. So the derivative of x plus the derivative of 1. Well, the derivative of x is 1 and the derivative of 1 is 0. So I do believe that g of x, g prime, I do believe that g prime of x is just going to be 1, I'm pretty sure. Um, so, so that means, so what that means is that the derivative of ln of x plus 1 is going to be 1 over x plus 1 times 1, which of course is just going to be 1 over x plus 1. All right. And so let's just take a moment to just sort of reestablish ourselves. All right, we got to reestablish ourselves because this is going to be the limit as x approaches infinity. Um, and we need to we need to put what we had. So the derivative of the numerator, natural logarithm of 2x. And what did we find for that? We found, uh-oh, I think I might have messed something up. No, we don't want to leave that alone. Don't worry about this. This is not, we're not going to worry about this right now. That's not, that was a mistake. But I'm leaving the mistakes in here because you know what? Luckily that was a mistake in the final computation, so everything didn't get destroyed. But that was a simplification error because I want to leave it in that 2 over 2x form. But I am gonna leave the mistakes in here just because you know what? Like I'm not perfect, and I'm not gonna sit here and pretend like I am. Um, I'm an idiot sometimes. I am I'm yeah, but I don't have to go on, but I just believe me, I am. So 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 yeah, so we're just gonna plug that in because this is the derivative. This is the derivative. All right, 2 over 2x is in fact the derivative of the natural logarithm of 2x, okay? Which technically speaking, I could I could leave it, oops, I could leave it in this form. Or I could put it in 1 over x. But I don't want to because I know what's going to happen. I know what's going to happen. So this is technically correct, but but we don't want that. So it's technically correct, but it's like not, it's of a different form, right? I'm pretty sure. I'm pretty sure. Yeah, but I'm gonna leave it in that form. I don't want it in that form. Honestly, I'll leave it there, but just know that I'm using this because that implies that this is an error. It's technically not an error, but I know what's going to happen, so I'm going to use this one here. All right. So basically, we got 2 over 2x in the numerator of this complex fraction. All right. In the denominator of this complex fraction, well, we've already calculated the derivative of natural logarithm of x plus 1 to be 1 over x plus 1. So we have 1 over x plus 1 in the denominator. All right. That's okay. But what we have to do is reciprocate because we do not want a complex fraction. So that's going to be x as the limit as x approaches infinity for this complex fraction, reciprocate, which we are going to reciprocate x right here, x, and then x plus 1. Yeah, yeah. Okay, I like that. And then we're going to have the limit of x as it approaches infinity of well, this is going to be 2 times x plus 1 over over 2x. Okay, I'm going to I'm going to factor this denominator. This is going to don't get weirded out by this, guys. This is just going to be just a little bit of algebraic manipulation here because you see how I have this 2 factored out? I didn't distribute it on purpose. This is the reason that I wanted to use it with this orientation here is because if I factor out this 2 here, look at this, if I factor out this 2, x times 1, what do we got going on? Well, this is some cancellation that we could do with these 2's. So, and so what that means is that we're going to have the limit as x approaches infinity um for x plus 1 over x. All right, and so um there's a couple of different ways that we can go about this because here's the issue, right? There's an issue, and I'm gonna move this up. This is another indeterminate form, right? Because if we plug in for infinity, um, we're just gonna get infinity over infinity. So there's 2 ways we could go about this. We could apply L'Hopital's rule again. We could take the derivative of the numerator and the denominator again. Um, we could take the derivative of the numerator and the denominator again, or we could manipulate it with algebra. Let's go the algebraic route. I want to do some algebra. Um, because there's 2 different ways that we could go about this. There's 2 different ways that we could go about this algebraically. Okay? The first way, the first way is that you could split up the fraction. You could say, okay, well, x plus 1 over x, well, that's going to be the same thing as, x over x, right? Plus 1 over x, and that's going to be the same thing as 1 over 1, or excuse me, that's going to be the same thing as 1 plus 1 over x, okay? And so then we're going to have the limit as x approaches infinity um for 1 plus 1 over x, okay? Or if you're really clever, right, you could do the you could take the limit as x approaches infinity of x plus 1 over x with we can divide by the highest degree in the numerator and the denominator. So really what I'll do is I'll multiply. It's the same thing as division because it's a fraction, but multiply 1 over x 1 over x. I like to think about this as a mathematical trick shot, but, you know, call it whatever you want. The limit of, 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 sorry, I was just trying to think about something. This is going to be x over x plus 1 over x in the numerator, and the denominator is going to be x over x, or 1. Okay, so if you turn this here into 1, so really you just be like, the limit as x approaches infinity, running out of room here, but it's going to be 1 over, excuse me, 1 underneath 1 plus 1 over x, or the limit as x approaches infinity of just 1 plus 1 over x. All right? And so, if we plug in infinity, right, like if you plug in as x approaches infinity for 1 over x, if you plug in infinity for x, the numbers are just going to get really, 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 really small, and that's going to equal 0. So this is going to end up going to 0. 1 over x is going to go to 0 for the limit as x approaches infinity. And so what's going to end up happening is we're going to have the limit as x approaches infinity is going to be it's going to be 1 plus 0, and that's going to equal 1. And since 1 is a finite number, the sequence here converges. And so the answer is that the sequence converges. I'm gonna just do math until I fall asleep. But basically, so this here is a series, okay? And and so say you're given this geometric series and you're prompted to put it into sigma notation. They say put this in the sigma notation. And then they say to find the value of the series and to find out if the series diverges. And if it does diverge, you have to explain why. All right. So when you look at this, you they already told you that it's a geometric series. Okay. So geometric series. Let a not equal 0, and a is always the first term in the geometric series, and r is real numbers. Okay, so if the absolute value of r is less than 1, then let's see, right, sigma right here, then let's see, k equals 0 to infinity. The series is k equals 0 to infinity of a times r raised to the power of k equals a over 1 minus r. And if the absolute value of r is greater than 1, the series diverges. All right, so you're given a geometric series, right? The geometric series looks like this, and if the absolute value of r is less than 1, then the series converges. Write that in, converges to this value here specifically that you can find. All right, if the absolute value is greater than 1, then the series diverges. All right, now here, the first term in the series, let's say the first term of the series is 15. So a equals 15. All right, r, which stands for common ratio. Well, r, we could find r by taking negative 10, the second term in the series, and dividing it by the term that comes before it, which is 15, the first term of the series. All right? And negative 10 divided by 15 is going to be negative 2/3. Okay? Um, and so we'll just leave that there. So since r, not just r, but since the absolute value of r, since the absolute value of r equals negative 2/3, the absolute value of negative 2/3, then that's just going to be 2/3. The absolute value removes that negative sign away, and 2/3 is in fact less than 1. So what does that mean? Well, that means that the series converges. The series converges, and we can find that the series converges to a over 1 minus r. And a over 1 minus r, well, a is 15. Okay, then 1 minus r, which is going to be negative 2/3, so it's going to be plus 2/3, right? And let's see, we're going to have 15 over a form of 1, 3 over 3 plus 2 over 3 equals 15 over 5 over 3. And then we will reciprocate 15 over 1 times 3 over 5. Let's see, 15 times, let's say 15 times 3 is going to be 30, 45. And that's going to be over 5. And then 45 divided by 5, I think it's 9. So the answer is 9. So the series converges, so the geometric series, and then we have to write it in sigma notation. They want us to put it in sigma notation specifically. So it's going to look like this. So we're going to have our sigma, and then it's going to be k equals 0, and then we're going up to infinity. The a, right, AR, so a, the first term in our series is 15 times the ratio, the common ratio, which is, we found it to be negative 2/3. And then k is just going to be k. Oops, k. And then this is going to converge to 9. And our answer is 9. And so this is going to be our full answer. And the series converges. All right? Say we're given a series starting at k equals 2, and we're going up into infinity. And the series is the natural logarithm of k over k squared. Okay? And we're told that we need to use the integral test to determine whether or not the series converges or diverges. So, does it converge? Let's find out via the integral test, which has lots of constraints to be able to use. So, the first thing to do when you want to check to see if you can use the integral test to see if a series converges or not is that you take f of x and you set it equal to the function, but instead of k, you put x, right? X, so natural logarithm of x over x squared, where f of k equals a sub k for, let's see, k starts at 2, so k, 2, 3, 4, and so on. All right? And so we need to ask ourselves, like, Is f of x continuous? Is it continuous? Well, f of x, ln of x over x squared. Yes, that's continuous. Well, that's continuous for on the intervals of 0 to infinity. So 0 and infinity, so yes, right? Yes, it's continuous on um it's continuous on 0 and infinity, on the interval 0 and infinity. So yes, it's also going to be continuous on 2 and infinity. All right? That checks out. Let's do the next one. Is f of x, we have to ask ourselves if we want to use the integral test, is f of x positive? Is it positive? Um, well, let's check really quickly because ln of x over x squared, um, well, that's greater than 0. All right, and ln of x is greater than 0. Okay, so this is true. This is um, true for all x is greater than 1. So then so on, so on 2 and infinity, yeah, yeah. Okay, now we have to ask ourselves, like, is f of x, is f of x decreasing? Is f of x decreasing? So there's two ways that we could do this. We could graph it with our graphing calculator, like a TI-84, or we could use Desmos, or we could take the derivative of the function. And the derivative of the function is decreasing. It's decreasing when f prime of x is less than 0. Um, so let's differentiate. Why not? Let's differentiate f of x equaling ln of x over x squared. So why not, right? We have what do we have? We'll start with f of x equals ln of x over x squared. Okay, and we're like asking ourselves, we're like, okay, but like what's f prime of x though? All right, so we have to use the quotient rule. We have to use the quotient rule to find this. So d over dx. So the derivative of some function u of x over um over over v of x is going to equal, so find the derivative of some function u of x over some function v of x is, well, that's going to equal u prime of x times v of x minus u of x times v prime of x. And this is all going to be over, v of x squared. Okay? This here, this is the quotient rule for this is the quotient rule for differentiation. Um, yeah, this right here, this is the quotient rule for differentiation. So box it up the way we do. And then now we're gonna have to identify, like, what even is u of x? Like, what is that? What is u of x? Well, for us, u of x is on top, and that's gonna be ln of x. All right, so ln of x here. And then we know that the derivative of ln of x, so u prime of x, well, that's just going to be 1 over x, okay? So then the derivative of v of x, excuse me, v of x, let's not get ahead of ourselves. Well, there. V of x is going to be x squared, all right? But then the derivative of v, the v prime of x, right? The derivative of x squared, let's see, the power also is going to be 2x, right? Now we just plug back into our formula. We just plug everything back in. So it should look like this, I think. It's going to be f prime of x equals 1 over x times x prime minus ln of x times 2x, right? 2x. And this is going to be all over x squared over, no, excuse me, x squared times, no, yeah, x squared raised to the second. And so that's going to be, um, well, it's supposed to be a 2, excuse me. So this is going to be x squared over x, okay? And then we're going to have minus 2x times ln of x. And then in the denominator, this is just going to become x raised to the power of 2 plus 2. Okay? Now, something more could be done. Well, these are going to cancel. Say we have like a 1 up here that looks like an x. Let's leave that alone. Let's just rewrite that. I don't want any confusion. Um, well, so this is going to be x, because this x is going to cancel out. So it's going to be x minus 2x times the natural logarithm of x over x raised to the fourth. And then what we can do is we can actually factor out an x from the numerator. So it'll be like x times 1 minus 2 times the natural logarithm of x, right? And then all over x to the fourth, but then we'll find that this is going to cancel with this. So then really we're going to have 1 minus 2 ln of x over 1 minus 2 ln of x over x to the third, I think. All right. But then now we want to check that f prime of x is going to be less than 0, right? And and since and since for so I'll say that since for x being greater than or equal to 0, um, x raised to the third power is greater than 0, and the denominator is positive. So the sign of f prime of x, it depends only on the numerator, and the numerator is 1 minus 2 times ln of x, right? And so to make f prime of x less than 0, we need we're gonna need 1 minus 2 ln of x to be less than 0. Okay? So what we have to do now is we have to solve the inequality. So I'm going to subtract 1 from both sides. I'm going to subtract 1 from both sides. It's going to be negative 2 times ln of x. Negative 2 times ln of x is less than negative 1. And then I'm going to divide both sides by negative 2. And when you divide by a negative, or if you multiply by a negative, but in this case, if you divide by a negative, the sign of the inequality flips. So, so those guys are gonna cancel, and these actually these negative signs are going to cancel as well. But the inequality sign is still going to flip. So this is going to be ln of x is greater than 1/2. And now we're going to exponentiate both sides to get um to get to get x by itself, right? So we want to get rid of the natural log, and we're going to use Euler's number to do so because they're inverses of one another. So we have Euler's number raised to the power of ln of x, right? Exponentiation is greater than e raised to the power of 1/2. Okay, but then of course these are going to cancel. Okay, so now we have x by itself. Okay, so x is greater than e raised to the 1/2 power, and and anything raised to the 1/2 power is the square root, right? So x is greater than the square root of e. So that means in conclusion that f prime of x that f prime of x is less than 0 whenever 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 x is greater than um, the square root of e, and the square root of e approximately is equal to 1.64, I don't know, 8 something, but 1.6. Okay, cool. But we're interested like for the interval of the integral is the integral of the integral is going is 2 infinity. All right, and let's see here, and 2 is greater than the square root of e, and it follows that for all of x being greater than or equal to 2, that f prime of x is going to be less than 0. All right, so that means that f of x is going to be f of x is decreasing on the interval 2 to infinity. Okay, so what that means is that we can use the integral test. This is the proof that we need in order to be able to use the integral test. So we're good to go at this point. So I'm going to delete all of this, and we're going to now actually do the integral test. Honestly, I'll leave that. I'll leave that alone. Okay. So here's how this is how this is gonna go. We have like the definite integral from a to infinity f of x equals, oh no, excuse me, oh, f of x integration with respect to x. My apologies. Equals the limit of b to infinity of the definite integral from a to b of f of x integration with respect to x. All right. So then this is how this is gonna go. Well, we have the definite integral, right? We're starting at k equals 2, so it's gonna go from 2 to infinity of the natural logarithm of x over x squared integration with respect to x. This is an improper integral. Now to manage this improper integral, we're gonna take the limit, right? The limit of as b approaches infinity, um, and this is going to be the definite integral. This is going to be the definite integral of 2 to b um, of x. We're going to bring up that x from the denominator, x raised to the second power of times ln of x, right? And then this is going to be integration with respect to x. Okay. To solve this, this is going to use integration by parts. We have a product here, and we're gonna use our integration by parts, which I've learned the mnemonic device: ultraviolet, super, voodoo. Hold on, that's a V. I gotta be very clear. This is a V. This here is a V. Voodoo. All right. So now we need to identify what we're gonna set our u equal to, but we have to do so with Liate. And Liate, it goes like this: logarithm, inverse trigonometric function, algebraic, trigonometric, and exponential. And that shows the precedence and the way that we're going to assign u. So L is logarithm. Well, we see the natural logarithm, which is in fact the logarithm. So we have u is set to ln of x. The derivative of ln of x is going to be 1 over x dx. Okay, and then we need to find uh, we already have. So u is set to ln of x, and then v dv, let's see, it's going to be x raised to the power of negative 2. X raised to the power of negative 2, and then we have to find v. So to find v, we have to integrate. So to integrate that negative, um, honestly, I don't think I can do this in my head. Um, I should be able to. Maybe I can. No, I can't. Okay. Let's see. X raised to the power of n. Integration with respect to x is going to be let's see, x n plus 1. I should be able to do this in my head. But I can't. So um so this is going to be x. So um negative 2 plus 1. Oh, okay. I see what's going on here. And then this is going to be negative 2 plus 1, and this is going to give us negative x minus 1. Excuse me, negative x raised to the power of minus 1. So negative x raised to the negative power, raised to the power of negative 1. And so, honestly, like, I'm gonna just get rid of that because, like, we don't really need this, like, up here. Because we have what we need, our components for integration by parts. So then we'll do U, ultraviolet, which is going to be negative x raised to the power of negative 1 ultraviolet minus the integral of super and then uh, voodoo. So negative x raised to the power of negative 1 vu, and then this is going to be times 1 over x integration with respect to x, right? And then we can like simplify that more, I'm pretty sure. But I think we might want to put that first, that I think that we might want to put the first terms into, well, here, let's start here. Let's do this. This is all within a limit, okay? This is all within a limit, and we can't forget that. So it's going to be the limit as b approaches infinity, negative x raised to the power of negative 1 times the natural logarithm of x plus the definite integral, because this is a definite integral, um, which we could address at the end, but you know what? Let's just pedal to the metal here. So the definite integral from 2 to b plus Um, mm, hold on, I have to think. I'm like not, I mean like, okay, because, mm, mm, okay, I see. So I'm gonna move that to the denominator. So this here, I'm gonna factor out that negative, okay? So this negative here, it's gonna get factored out. And then that's why this is gonna become a plus. Then we're gonna have 1 over x times 1 over x because I'm going to move that x into the denominator to get rid of that negative exponent, right? And then I think, and then I've got to integrate. Mm, so what? This is gonna be like the limit. I might have to mess around with this for a minute. Hold on. The limit of uh negative x raised to the power of negative 1 times ln of x plus the definite integral from 2 to b. Um, well, this is going to be 1 over x squared integration with respect to x. I'm going to have to play with this. This is going to, yeah, no, because I'm going to, yeah. Okay, so the limit as b approaches infinity, of negative x raised to the first power, the negative first power, times the natural logarithm of x plus the definite integral from 2 to b for bringing that up from the denominator because now I'm going to evaluate this with the power rule. So let me try to do this one in my head. I think it's going to be like this. I think this is what I said. Okay, okay. So negative 2 plus 1 is negative 1, so it's raised to the negative first power, but then underneath it's going to be negative 2. It's going to be negative 2 plus 1, right? And that's going to be negative 1, so we bring out a negative, and then it's that if I put that back in the denominator, so it's going to be the answer to this here, it's going to be, negative 1 over x evaluated from 2 to b. So it should, I think it should look like this. I think that this is what it's going to look like entirely. The limit as b approaches infinity for the natural logarithm of x raised to the power of x minus 1 over x evaluated from 2 to b. Yeah, I'm liking that. Okay, so then, and so then, what that means is the limit as b approaches infinity, we're going to evaluate this via the fundamental theorem of calculus, part 2. So it's going to be the negative rational expression of the natural logarithm of b, right? And then over b minus 1 over b, okay, minus what we get when we plug in the lower bound. So that's going to be negative, um, the negative rational expression, the natural log over natural logarithm of 2 over 2 minus 1 half. Um, and then let's just check this out here. Let's just analyze this for a second because as you plug in infinity, oh my gosh, wait a second. This is gonna go to 0. Yeah, that's gonna go. Okay, that's cool. Okay, this is gonna go to 0. This is gonna go to 0. Oh yes. And then I think we should distribute this. I think we should distribute this. And then so this is gonna equal 1 over 2 times the natural logarithm of 2 plus 1 half. All right, so 1 half times the natural logarithm of 2 plus 1 half. And this means that the integral converges. And it converges to this here. All right. So therefore, by the integral test, the series from k equaling 2 to infinity of the natural logarithm of k over k squared converges. Okay, imagine that we have this infinite series. It starts at 1, it goes to infinity for k squared over 4 raised to the power of k. And we want to know, like, does this series converge? Does this series converge? Does it diverge? And how can we find out? Well, in order to be able to tell whether or not the series converges, we're going to use the ratio test. And I know that we're going to use the ratio test because there is a term that's being raised to the power of k, and that's how I know that's a good indicator for um, us using the ratio test. The whole thing is not being raised to the power of k, just this term here is being raised to the power of k. So we're going to use the ratio test in order to test to see if this series is convergent or not. And the formula for the ratio test is written as follows. So this says that the ratio is equal to the limit as k approaches infinity for a sub k plus 1 over a sub k. Now, the series, it converges absolutely if, so I'll say the series converges absolutely if, um, if r is less than 1. Okay? So the first thing that we're gonna have to do is identify, like, what is a sub k? What is a sub k? Well, a sub k is right here. A sub k is the function in the series. Um, so it's right next to the sigma. So that would mean that a sub k is k raised to the second power over 4 raised to the power of k. All right, but we need to find um what a sub k plus 1 is. What's a sub k plus 1? Well, in order to find what what a sub k plus 1 is, um we need to replace k. We need to everywhere we see a k in this expression, we need to replace it with k plus 1. So we don't have k squared anymore. We have, I should probably put some parentheses, k plus 1 squared, right? That's what we get for a sub k plus 1. So we don't have 4 raised to the power of k anymore. We have 4 raised to the power of k plus 1. And that's how we can have case that's how we can have a sub k plus 1. And then the next thing to do is to set up the ratio, right? Because we need to find the limit of the absolute value of a sub k plus 1 over a sub k. Well, we already know what a sub k plus 1 is, and we have that right here. So we'll go ahead and we'll set up the ratio for this. And I want to be very clear. I want to be very clear. So I'll write out a sub k plus 1 and a sub k in the denominator. So, um, well, so for a sub k plus 1, we set that equal to k plus 1 raised to the second over 4 raised to the power of k plus 1. All right, and this is a complex fraction, right? So we're going to do our a sub k in the denominator, and that's going to be k squared over 4 raised to the power of k. And in order to get this to not be a complex fraction anymore, we're going to reciprocate. And so that's going to look like this. K plus 1 squared over 4 raised to the power of k plus 1 multiplied to 4 raised to the power of k over k plus 2. So same sort of idea as before when we use the ratio test. We're going to multiply this and then regroup. So this, of course, is the same thing as k plus 1 raised to the power of 2 times 4 raised to the power of k, and that's all over the denominator 4 raised to the power of k plus 1 times k raised to the power of 2. So we're going to get the k terms together, and we're going to get the terms with a 4 together. We're gonna regroup the fraction. We're gonna reorganize it, right? Um, so the first thing to do here, I will say, the first thing to do, um, well, I'll say that we're gonna have k plus 1 raised to the power of 2 over k squared, okay, and then that's going to be multiplied to 4 raised to the power of k over 4 raised to the power of k plus 1, okay, and then each part it's going to get simplified. So let's see, how do I want to lay this out? Let's just put a comment here. The first thing that we're going to do is I'm going to simplify this expression here. So to be very clear, I'm going to simplify k plus 1 raised to the power of 2 over k squared, and this equals, um, well, we could just pull out that 2 altogether and just make this rational expression on the inside of the parentheses absent of the power of the second degree, and we'll just bring that outside the parenthetical statement here, and so now that's the same thing as, well, we could split the fraction, so let us do so. I do believe that, well, here, we'll do k over k plus 1 over k, all right, raised to the power of 2. And k over k, of course, is just a form of 1, so really we have 1 plus 1 over k. And, oh yeah, and this is going to be squared. And then for the second one, because we gotta simplify this guy here, um, well, so I think, so here what we could do is, um, well, I think I ought to utilize this room over here. Let's see here. Now we got 4 raised to the power of k over 4 raised to the power of k plus 1. Okay. So I'm going to bring this up from the denominator. I want to bring this upstairs. So I'm going to grab this 4, and then in the exponential place, we're going to have k minus k plus 1. But of course, that negative sign is going to get distributed into this binomial here. And it's what we're going to end up having is we're going to have 4 raised to the negative first. And 4 raised to the negative first is the same as 1 over 4. And well, so that's going to mean that so for that's going to mean that so like if I have a sub k plus 1 over a sub k, well that's going to equal that's going to equal 1 plus 1 over k, and this is going to be brought up to the second power, and then we're going to multiply this to 1/4. And that's what the simplification of that's going to look like. But now we're going to have to take the limit. We don't really so much need to worry about the absolute value symbol because this is positive. This is going to be positive. So let's go ahead and we're gonna find that ratio here. We're gonna find that ratio. So we're gonna take the limit as k approaches infinity, and that's going to be 1. So the limit as k approaches infinity for 1 plus 1 over k raised to the second power times 1/4. Okay, so let's just analyze this really quickly now. As k as k approaches infinity, as k approaches infinity, um, for 1 over k, if we plug in infinity for 1 over k, it's just going to get really, really small, right? As you plug in, let's see. Yeah. So really this is going to just be 0. All right, this 1 over k, it's just going to go to 0. And um, and so what that means is that the ratio itself, is going to be I think it's 1 plus 0 raised to the second times 1/4. Okay, and then well that's just going to be, well, and then we're going to move over here. We're going to be r equals 1 plus 0. I'm sort of just rewriting this. I already started, might as well finish. But this is going to turn into r equals 1 raised to the power of 2 um, times 1/4, and that's just going to turn into r equaling 1/4. So r equals 1/4. And then when we look at this, r equals 1/4, well that's less than 1. And if r is less than 1, then the series converges. Therefore, the series converges absolutely because, well, I'll say that the series converges absolutely by the ratio test because 1/4 is less than 1 and 1/4 is the ratio. And so the series converges. Okay, so we have this infinite series here from k equals 3 to infinity of 2k over k squared minus 4. And we want to know, does it converge? And we are allowed to use whatever convergence test that we want, right? So does it converge? Um, so I think um, the best bet is to use the limit comparison test. And the limit comparison test is a comparison test, but it's got to do with limits, right? So let me just go ahead and write it out. I'll say limit comparison test. Um, so it's the limit of as k approaches infinity of a sub k and b sub k, and it equals L. And such is true if 0 is less than L and L is less than infinity. Right, so if 0 is less than L and L is less than infinity, then both series that are being compared, both of them, they stay the same. Or excuse me, they behave the same. This is the limit comparison test. And the idea here is to compare um, what we have in our series to a simpler series that we already understand. Like, for an example, right? We understand the P series. We understand the P series. We know that the P series, it's well, it's let's see, we got sigma 1 over k raised to the power of p. And the P series, um, the P series converges if well, the P series converges if P equals excuse me, if P is greater than 1, and it diverges if P is less than 1. All right, we understand the P series. We know about the P series, right? And we also could compare it to, for an example, like the harmonic series, right? We understand the harmonic series. Well, enough for this, right? Harmonic series. We understand its properties in the sense that the harmonic series, let's see, the harmonic series is 1 over k, and we know that the harmonic series diverges. So we know about it enough to know that it diverges, all right? So the idea is to compare what we have to a series like the P series, which we understand, um and the harmonic series, which we understand. And so, well, with respect to whether it converges or diverges, or what constraints and properties it has in order to determine whether or not it um converges or diverges. I mean, that's really specifically with the P series because the harmonic series always diverges. Anyway, so um well, let's look at 2 times k over k squared minus 4, and let's just approximate this, because we could just like ignore we could just ignore that negative 4, because as k gets really really big, like what is the negative 4? Like, it's already, we have k being taken to the power of 2. The negative 4 is kind of negligible, especially as k gets bigger. So we're just going to say that this is 2 times k over k squared, right? And then we're going to have some cancellation action going on here, and these k's are going to cancel. And so we're going to have 2 over k. All right. Now, 2 over k. Well, this looks an awful lot like um like the harmonic series, okay? In that we have 1 over k, and we know that the harmonic series um diverges. Okay? So when we're doing the limit comparison test, that means that we can set a sub k equal to 2k over k squared minus 4, right? And then b sub k, it's going to be 1 over k, because this is the harmonic series. All right? So we'll go ahead and we'll set this up. We'll say that L equals the limit as k approaches infinity L equals the limit as k approaches infinity of a sub k goes on top, a sub k over b sub k. Now we'll plug in our values and we're gonna have a complex fraction. So I'll try to just line this up so that we got enough room here, and I will um put a bracket just to try to keep it contained, but on the very top we'll have 2 times k over k squared minus 4, right? 4 is it? And that's going to be over the harmonic series 1 over k. All right, we'll go ahead and close this off. And so yeah, and so we're just going to multiply this by its reciprocal. So um, we got the limit as k approaches infinity. Okay, and then we have in these brackets here, we're going to do 2k over k squared minus 4 times k over 1. All right, and so upon multiplying, we're going to find that the limit as k approaches infinity, I think that this is going to be 2 raised to the power of k over k squared minus 4. All right, so now what we can do is well, we can evaluate this by just plugging in infinity. But the issue is that like if we just plug in infinity, like we're just gonna get an indeterminate form. Like we're gonna get infinity over infinity. All right. So instead, instead, what we could do is we could apply L'Hopital's rule, and we could take the derivative of the top and the bottom. But what we could also do is manipulate manipulate this algebraically by multiplying by 1 over k squared. Um, because k squared is the variable with the highest degree. So we could take the derivative of the top and the bottom, but we could also just write out the limit here. We could also just manipulate this algebraically. So um, let's do that, shall we? So we got 2 times k squared over k squared minus 4, and this is going to be multiplied to 1 over k squared times 1 over k squared. All right, and now what's this going to give us? Well, we're going to get the limit as k goes to infinity. I think, let me see here. K squared, so this is going to be, okay, so this is going to be like, I think it's going to be like this, like 2 times k squared over k squared over um k squared minus 4, and then we could just split these off into their own k squared on the bottom here for both of these guys. All right, and so what's going to end up happening is, well, there's going to be some cancellation here. All right, and this is just going to be 1. So maybe I'll just leave that alone. Well, in this in this section, but k as the limit, so the limit as k approaches infinity, um, well, this is going to be, I think this is going to be 2 over 1 minus 4 over k squared. And then and then you when you plug in infinity for k, well, the denominator is just going to get larger and larger, and so this is going to go to 0. 4 over k squared is just going to go to 0 if you plug in infinity. Um, so we got this is going to equal 2, right? And and since 0 is less than the limit, and the limit is equal to 2, and 2 is less than infinity, um, by the limit comparison test, right? Um, both series behave the same. So the theorem says that if the limit is greater than 0 but less than infinity, that both series behave the same. And the harmonic series is the one that we featured by the limit comparison test, and we know that the harmonic series diverges. So since the harmonic series diverges, and that's what we featured in the limit comparison test, that would mean that the series of k equaling 3 going up to infinity for 2k over k squared minus 4, that means that it also diverges by the limit comparison test. So the answer is that this series diverges. All right, so imagine that we have a series, right? And the series is from k equaling 1 to infinity for k times Euler's number raised to the power of negative 9 times k raised to the power of 2. How might we be able to tell whether or not the series converges or diverges? We can use the integral test. The only thing about the integral test is that it's a little bit fussy. There are constraints and conditions that need to be satisfied in order to be able to properly evaluate this by using the integral test, and we'll have to check we'll have to check that these constraints are satisfied. So I'm going to go ahead and rewrite the function. Say f of x equals x times Euler's number raised to the power of negative 9 times x raised to the power of 2, right? It's 2, yeah. So the function f of x, it needs to be positive. So I'll go ahead and say the function f of x. So is it positive for x being greater than or equal to 1? Um, is the function f of x continuous? Pretend that says continuous. Is it continuous for x being greater than or equal to 1? Um, does the function f of x have the property that a sub k equals f of k for k equaling 1, 2, 3, 4, etc. And is the function f of x decreasing? Pretend that says decreasing. Um, is it decreasing for I think it's x being greater than or equal to 1. So, well, let's just work through this here. So let's just go ahead and check. So the function f of x, well, f of x we know it's equal to x times e raised to the power of negative 9 times x raised to the power of 2, right? Um, so for x being greater than or equal to 1, well, x is greater than 0, and Euler's number raised to the power of negative 9 times x raised to the power of 2, well, that's also greater than 0. So that would mean, well, that would mean that f of x is greater than 0. And it's continuous. We know that it's continuous because, well, x is a continuous function, and e raised to the power of negative 9 times x raised to the power of 2, um that's continuous. E raised to the power of negative 9 times x raised to the power of 2 is continuous, and also um um a sub k equaling k times e raised to the power of negative 9 times k raised to the power of 2, that equals f of k, and that's going to also be decreasing for x being greater than or equal to 1. So what that means is that we can use some improper integral logic. So I'm trying to remember how the formula goes. I think we could just jump right into the limit, honestly. Or I guess the improper integral. So I think it goes like this. If we have a definite integral, if we have a definite integral and we're going from 1 to infinity of x times Euler's number raised to the power of negative 9 times x raised to the power of 2, and we're going to do some integration with respect to x. Um, I think that we could do, like, it's a product, right? So like I want to be like integration by parts, but I think we can actually do u substitution. So if we substitute and let u be equal to um negative 9 times x raised to the power of 2, then we can find the derivative of that. Um, so we'll set negative 9 to the side. Negative 9 to the side times the derivative of x raised to the power of 2, and we could just do that in our head, right? Because the 2 is going to come out front, and it's just going to be, well, it's actually going to be negative 9 times 2x, because that's going to be the derivative. 2x is the derivative of x squared, I think. So I think it's going to be like this, negative 18, ooh, negative 18, um, times x. Negative 18 times x integration with respect to x. We just took the derivative. But the issue now is that we don't have a negative 18 in our integral here. So, well, if we divide this by if we divide this by negative 18, we divide this by negative 18, um, right? I think we divide it by negative 18. Negative 18 du equals, well, now that's just going to be x dx, and we do have an x dx in our integral here. Um, so what we can do, this looks kind of messy. It's a little bit impromptu. Um, uh, say the definite integral from 1 to infinity of um e. We're gonna leave the e alone, but we've set the exponent, e raised to the power of negative 9x squared set to u, so it's gonna be e raised to the power of u, and then um we have negative 18 negative 18 du, right? Negative 18 du in the place of where the x dx is. So, um, well, can we factor out the negative 18? Then we'll have the integral of 1 from 1 to infinity of e raised to the power of u du. And we know how to deal with this. We know how to deal with this. Sorry, I'm laughing because that integral, it looks, it's all wobbly. So, I don't know, my humor is broken. Okay, so then we know how to evaluate the integral of e raised to the power of something. Like, it's just going to be left alone. So if we go ahead and we integrate, we're going to be left with 1 over 18, negative 1 over 18, um, e raised to the power of u, and then our evaluation bar is going to say um, from 1 to infinity. And that's going to be uh that's just going to be 1 over negative 1 over 18 times e raised to the power of u evaluated from 1 to infinity. And then that's where the fundamental theorem of calculus comes through. Um, though I am running out of room here. Can I see, it's important though that I have these constraints here because they matter. So if I just did some of this, maybe I could just get a little bit of retail here. Yeah, let's roll with that. Let's roll with that. Um, so okay, so let's just look at this at x equaling infinity. If we look at this from at x equaling infinity, um, e raised to the power of negative 9 times x raised to the power of 2, right? Because we're going to have to evaluate at this at some point because we're going to plug in um we're going to plug back in. Oh, I didn't. Oh, okay. Let me just rewrite this really quickly because we have to back substitute. I want to be very clear. So negative 1 over 18 e raised to the power of u, which was set to negative 9 times x squared. And that's going to be evaluated from 1 to infinity. Okay, so then now, right, we're at some point, we're gonna have to evaluate this. But no matter what we plug in, be it 1, um, look at 1, yeah, this is gonna go to 0. Because this is called exponential decay. This is just gonna go to 0. So that would mean that, let's go this way. That would mean that negative 1 over 18 times e raised to the power of negative 9 times x raised to the power of 2 is also going to it's just going to go to 0. It's just going to go to 0 at x equals infinity. Oh. Okay, wait, I'm sorry, because before I said 1. So let me just recalibrate here. So why don't we just make it here? I'll make this more clear. So negative 1 over 18. And we're just going to do some fundamental theorem of calculus, part 2. Um, e raised to the power of negative 9 times infinity, right? Times infinity raised to the power of 2 minus, well, this is going to be plus, right? Because it's going to be, we're going to have to plug in the function. So plus 2 minuses means a plus. So plus 1 over 18 times Euler's number raised to the power of negative 9 times 1 raised to 2. Okay. So yes, at x equals infinity, if you plug in infinity here, so increasing numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, like and on, well, that's just going to go to 0 because there's a negative here. This is known as exponential decay, so this is going to go to 0. At 1, if we just evaluate this as 1, so in essence, we're going to have plus 0, whatever this is. So whatever this turns out to be, it's just going to be plus 0. So we're going to add a plus 0 to it. But if you plug in like a 1 here, it's just going to be 1 raised to the power of 2 is just going to be 1 times negative 9 is just going to be negative 9. So what we're going to end up with is 0 plus 1 over 18 times Euler's number raised to the negative 9th power, which we can rewrite as Euler's number raised to the negative 9th over 18. And so that's gonna mean that the series, oh, my cat's here. Hi, Theta. Hi. My cat came to visit. Okay, go over there. Thank you. All right, so where was I? Um, she's coming back. She's coming back around. Okay, wait. So yeah, okay. So this is what the series converges to, and so that's gonna mean that the series converges. Um, and if I don't really have any room here, but here I'll just write it up here. Say this. Um, so the conclusion will be at the top. If the definite integral from 1 to infinity of f of x, integration with respect to x, converges, which it does, well then that means that the series of k equals 1 to infinity of that function, call it f of k here. Well, that means that this too converges via the integral test. And so that's going to be our answer.